All right. Hello, everyone. um, I hope you can hear me well. I'm trying to see if, because I don't really have a microphone. All I have are like these earbuds, these headphones. And so now I'm trying to see if everything is set up correctly. I think it is. Hopefully it is. If it's not, please let me know. Um, I am trying to have sort of the stream here open on the side so that I can be aware of like how things are looking and whether or not things are working. Um, on my screen, it doesn't seem like it's changing. There's something weird on my end. Like my whoa, it showed up now. All right. uh Perfect. Welcome everyone to the stream. Um, if you are wondering, sure, did you get a haircut? No, I did not. And all I did was just, put a little bit of water on my hair because it was a little bit crazy. So you're gonna see me do this all the time because the hair is falling due to the water. Today, today, ladies and gentlemen, and everything in between, we're going to continue working on our memory allocator. Now, if you remember correctly, 2 days ago, which was my first time on Twitch, we started with the design of the memory allocator, and that design looks something like this, right? Look at this beautiful transition. Whoa! Right? Spent some time doing that between the first day and the second day, and now I figured out OBS. Now I know how to do this. There we go. So just to recap to everyone, if you're new to the stream or like if you were in previous sessions and are now revisiting, this is the design we settled on for our memory sort of blocks, right? Whenever we need to allocate something, a sort of the piece of memory is going to look like this for us. We're going to store the size of sort of this block, the left child, the right child, the parent, and the color. You may be asking, Sharif, what are these things? What is left, right, parent, and color? And the answer is going to be precisely revealed in a few seconds after you look at this thing over here. We decided that the memory allocation policy that we're going to follow is best fit. Just because of considerations we were making, we ended up designing best fit. And data structures available there are many, right? But in terms of searching, the first thing that comes to mind is a binary search tree, and it's in fact one of the more efficient data structures to perform search. And binary search trees can be improved through AVL trees or red and black trees. And between those two options, red and black trees represent a better memory usage. And that's the reason why we have these members here. Left child, right child, parent of the node, and color of the node as it respects to red and black trees. So once we had that, and by the way, we also had ZM's idea on how to sort of store the color in the last 2 bits of the parent, given that all memory, sort of all blocks are going to be aligned by 4 bytes. We can simply, out of any of these fields, ignore the last 2 bits once again, since anything they point to is going to be aligned by 4 bytes. So those last 2 bits, the least 2 significant bits, are not going to be used, and we can simply ignore them, and we can just store color in that least significant bit, thus saving sort of 1 bit, yes, but not only that, we save on alignment, because having this extra field, we cannot just store 1 bit, we would have to store the entire byte, and that would mean that we offset the user data by like 1 byte, and now alignment messes everything up, and so this was a great idea. After that, we started saying, okay, red and black trees, great. The problem with red and black trees, ladies and gentlemen, is that I had heard of red and black trees. I knew they were a thing, which is the reason why we wrote them here, right? Because I knew of their existence but I've never really implemented one. And I don't really know how they work in like a very good way, right? I understand the principles and everything, I understand the idea behind them, but sort of really understanding how they work was something I was lacking that first day. So during the second day, we started our quest. Our quest to building a red and black tree implementation from scratch. And this is what we have so far. We have our red and black tree class. So, well, we have a struct that stores the node, and then we have our red black tree class. And we're going to support three main methods: insertion, finding something, and then removing something. For insertion, insertion was a little bit difficult just because of the rules of red black trees, but we ended up succeeding yesterday. And some of you may remember the moment where we finally succeeded with insertions, where all the test cases passed. We now, so the code just kind of looks like this, right? We went through, finding the point of insertion and then treating every single case related to red-black trees very carefully. And we finished insertion, great. We also finished yesterday find. So find was another one, but find was relatively easy to implement. We implemented it in like 10 minutes. And finally, we only need to implement removal. Removal from a red-black tree seems to be a relatively hard task, right? And that is not said by me only, it's also said by every single guide you go to on either YouTube or the internet. So we are in a little bit of a conundrum. Because today's stream is maybe not going to be as entertaining or because our goal for today is to write the remove function. Okay? We need to write the remove method. Once we achieve that, we can be happy. And it's going to be sunshines and rainbows after that. But it's going to be a very difficult path. And we're going to have to go through the 7 circles of hell, or of red-black trees, I should say. And finally, after all that suffering, once we get out of there, it's going to be really satisfying. But in the meantime, we are going to question our decisions a lot. So bear with me and start with me this journey of us writing the memory allocator. All right. So first thing we will need to do is we need to pull up a guide, some sort of guide. And I have right here Firefox. Some sort of guide on red-black trees, which I think red-black tree deletion makes this like a very common thing. And we have some blog here, right, by Swati Rajwal. So hopefully I pronounced this correctly. And we are going to take a look at removal in red-black trees. Once again, this is going to be mainly us reading all the specification for red-black tree, what they are. Oh, well, no, like we know what they are and everything because we already implemented insertion and find. But now we need to implement deletion. So yeah, bear with me and let's learn together, I suppose, because I also know nothing about them, at least in this case of deletion. So let's read this, let's see. Deletion of a red-black tree is a bit tricky than other binary trees. So great start. 30% the delete operation with suitable examples. Okay, prerequisites, you should have some knowledge about operations performed on a binary search tree. We already sort of know this. We know how the insertion operation works on a red-black tree. You should be familiar with terms like sibling, parent, grandparent of a node. Yes. Quick recap for those of you who maybe were not in the previous streams. A red-black tree is a binary search tree with 1 extra bit of storage per node for its color, either red or black. The tree is approximately balanced. Every node is either red or black. The root is always black. Every leaf, that is every nil, is black. And if a node is red, then both its children are black. And for each node, all simple paths from the node to descendant leaves contain the same number of black nodes. Those rules are so important that they dictate the behavior of a red-black tree, and they are written in stone in the comments of our code, because we really will need to revisit them. Sort of the motivation for a red-black tree seems we already have this a little bit clear. Just one thing to note is that whenever we consider sort of these nils to be a node in the tree, and that's what we call the leaf. And by the nils, we mean that in this case, for example, in this image, right? I'm trying to zoom in, but I cannot zoom in. There you go. In this image, if you can appreciate it, I'm not sure. You see how 17, 3, 21, and 32 compose the tree. But 3 has no children. Those children are sort of nil children. They just don't exist. It would be a null pointer. But we consider them to be part of the or part of the tree and have a black color always. Okay, that's the only thing you need to know. Now, every leaf node has a unique invisible child, called nil node. They are always colored black. Yeah, all in all, that's for all, Deletion cases, okay. This is what we're interested in. Always keep one thing in mind. A red-black tree should still remain a red-black tree after an element is deleted. Make sense? The below table is useful to identify the case and its corresponding set of actions to be performed. No need to remember it all. In this, DB stands for double black. Worry not. Below examples will explain what double black is. Just skip this table and jump to the next section. Come back to this table as and when needed. Okay, so we're gonna, the person that wrote the blog is the expert on this, so we're gonna obey their instructions. Maybe that makes things easier for us. Let's see, example 1, delete 30 from the red-black tree. Okay, I wish these images were a little bit better because I cannot really appreciate them very well right now. I hope it is visible in the stream. I personally can see it here on my end. I have the stream pulled up. Great. So yeah, let's see. Delete 30 from the red-black tree. So 30 would be this guy over here. You first have to search for 30, and once found, perform binary search tree deletion, assuming you know it. For a node with value 30, find either the maximum of the left subtree or a minimum of the right subtree and replace 30 with that value. This is BST deletion. Okay, that makes total sense. So we simply look for its in-order sort of predecessor or successor, and then we replace it. This is the usual way in which we delete nodes in a binary search tree. So that makes sense. And in the case of this tree, right, in the case of 30, we will simply go through the right subtree, find the minimum, which would be its immediate successor, and then just replace the node with that. And then delete 38. Yeah, perfect. The resulting red and black tree will be like 1 in figure 4. Element 30 is deleted, and the value is successfully replaced by 38. But now the task is to delete the duplicate element 38. See how we didn't delete 38 yet? Yeah. So now we have to delete that. Go to the table above, and you'll observe case 1 is satisfied by this tree. Whoa, okay. So this is the table. I'm gonna actually have it pulled up here on the side, I think, so that we can have it as a quick reference, rather than having to scroll up all the time. Yeah, here. So case 1, if node to be deleted is a red leaf node, just remove it from the tree. Well, okay, that's a great, I feel that applies to every node, but I know, okay, we know what they meant, right? Delete it as if it was a binary search tree, and we simply get rid of the duplicate now. Perfect. Since node with element 38 is a red leaf node, remove it and the tree looks like the one in figure 5. Oh, okay, I see. So actually it seems like what they meant was referring to this node over here. whether we're saying look at the table to know what to do with the node that we just replaced with the successor, right? That is now a duplicate. Okay, we'll see. Let's see. Observe that if you perform correct actions, the tree will still hold all the properties of the red-black tree, and we can see that in the example. Example 2, delete 15 from the red-black tree in figure 6. So 15 would be this guy. Notice now that the node that we want to delete is black, so this seems to be different. 15 can be removed easily from the tree. Simply, we perform binary search tree deletion. In the case of RB trees, if a leaf node is deleted, you replace it with a double black nil node. It is represented by a double circle. Okay, so something like this. So we delete 15, and then we mark that spot as double black. What does that mean? So the entire problem is now drilled down to getting rid of this bad boy, the double black, via some actions. Okay, so we don't like double black nodes, and we need to get rid of them. Checks out. Go back to our rulebook, and case 3 fits perfectly. Let's see what case 3 says. So have this tree in mind, take a mental snapshot, and let's go to case 3. If the double black sibling is black, yes, its sibling is black, and the double black sibling's children are black, yes, its children are black. Although it may seem like this guy doesn't have children, remember, nils count as children, and they are always black. So sort of in your imagination, you can picture how 30 would have a nil child here and a nil child on the right, both of them being black. So yes, case 3 fits. And what we do is, let's see, remove the double black, all right? If null, so it's our case, double black, then delete the node. And for other nodes, remove the double black sign. Well, if null double black, then delete the node. How are we gonna delete a null node? Am I just not understanding it correctly? Remove the double black. Yeah. If null double black, then delete the node. And for other nodes, so if the node is not null, then if the node has data, then remove the double black sign. This is confusing. I think we will look at how the example ends up, and then we'll figure it out. Make the double black sibling red, and if the double black's parent is black, make it double black, else make it black. Oh my god. The amount of cases we have to account for already making me want to cry, but it's okay. So it seems like we perform those steps, we remove the double black. I guess that means just stop coloring it as double black, because this guy is still gonna have a nil child, right? No matter what happens. Make the double black sibling red, so 30 would be now red. And if the double black's parent is black, that doesn't apply to us. Otherwise, make it black. So they would be 5 black, 10 black, 20 black, 30 red. And that's exactly what occurs. Okay. In short, remove double black and then swap the color of its sibling with its parent. Okay. You're getting pro already. See if you can solve the next example. All right. Well, okay. So let's look at this third example. Delete node with value 15. Okay. And as a rule, replace it with double black nil node as shown. Now, double black's sibling is black, and siblings, both children, are also black. So it satisfies all the conditions of case 3. Now let's look at case 3. So we remove the double black, so this guy just stops being colored as double black. Now we make the double black sibling red, so 30 is now red. And not only that, but if the double black's parent is black, we make it double black. So now the double black is going to be is contagious, and now it transfers to the father. So the parent is now going to be double black, so it's going to have a circle around it. 30 is going to be red. Everything's going to stay the same, and this guy's not going to show up anymore. Yes, okay. So after this, let's try and guess what happens next, sort of that we can understand what's going on. The double black is here. Let's see. Is it a leaf? No, that is not the node to delete, so never mind. If double black node is the root, no, that's not the case. If double black's sibling is black, so this is the double black, and its sibling would be 5. So yes, it's black. And both of its children are black, which is indeed the case. So we apply this case again. We remove the double black, so now 20 won't have the double black around it, and it will just be black color. We make the sibling red, so now 5 is going to be red. And then if the double black's parent is black, which is indeed the case, we transfer the double black to him. So it should be 1 and 7 remain the same, 5 is red, 10 is double black, 20 is red. 20 is black, 30 is red. Oh, okay, I thought they were about to put the article under a paywall, and I was gonna really mad, or really sad. But yes, okay, it applies. Perfect. And so let's still follow the table and see what happens. So according to this tree, the problem is going to be this double black over here. So if the double black node is the root, which was a case we had seen before, like while we were reading the table, so now we know that that case exists. The double black is indeed the root. What do? Remove the double black and root node becomes black. Okay? So I guess we simply color 10 as black. Perfect. The root resolved double black and becomes a black node, and you're done deleting 15 successfully. Great. We finished with that example. I feel it was a pretty good example. I like the way this article is written. It explains things extremely well. Kudos to the author, but these numbers should have been a little bit bigger because I know they're a little bit difficult to spot, but that's completely okay. Let's see, example 4. Delete 15. What do you have against 15? Okay. Delete 15 from figure 13. Okay, let's try and do this. So we look for 15, and we know that we just replace it for a double black since it's a leaf and it's black. If it was red, I think we can simply just, get rid of it or whatever. I don't remember the case. We have this tree over here. We end up with this guy on the right. And so now let's take a look at the cases. So we are double black, and let's see what happens. So if double black sibling is, if the node to be deleted is a red leaf node, no, that was not the case. 15 was deleted, but it was black. The double black node is not the root, so no. The double black sibling is black. Let's see. No, that's not the case. But case 4 tells us if the double black sibling is red, which is indeed the case, we swap color with double black's parent with double black's sibling. Oh, okay. Swap color of double black's parent with double black's sibling. So now the parent is going to be red and the sibling is going to be black. Then we perform a rotation at the parent node in the direction of the double black node. Okay, so after we change the color of these two, we rotate the tree to the left, which will put 30 as the new parent. So it's going to be 30 black, 20 red. The double black is going to still be there. And to the right of 20, it's going to be 25 as a black child and 40 as a black child of 30. Still. Check which case can be applied to this new tree and perform that action. Okay. So let's see. First, search 15 as per the BSG rules. Yes. Second, replace the deleted node with double black nil node as shown in figure 13. Sorry. Double black sibling is red. Clearly, case 4 is applicable. So indeed, we swap their colors. That's A. Then we perform the rotation. which will have this be 20 is the new parent, and 20 is now going to be the left child of 30, and 25 the right child of 20. Yes, so we perform the rotation to the left at the parent. Great. And then after that, the line is very confusing because it says, check which case can be applied to this new tree and perform that action, which is rather ambiguous, it seems. So the double black still lives there, right? So let's try and think about this. What do we have here? We have a double black. It is not the root. Its sibling is indeed black, and both of the siblings' children are black. So that means that we can remove the double black, so goodbye nil. Then we make the double black siblings red, so 25 is now going to be red. And if the parent is black, make it double black, else make it black. Okay, so we simply exchange the color of these two. So now we should be seeing in the next picture this guy black and this guy red. Okay, perfect. So this seems reasonable enough. Reasonable is a very subjective term for this because it definitely seems like a bit of a, a cascade of a bunch of stuff. But it is okay. I think we're starting to grab the concept. We're starting to understand it a little bit more. It seems like we just follow the table and according to that we act, which is great. And I mean, I guess that's every algorithm ever, right? Look at the table and then do something. Everything is a state machine in the end. But yeah, I know it's tiresome, but I swear if you practice these examples 2 to 3 times, you'll have a good grasp of the concept of deletion and red-black trees. Let's do one more example because these things are extremely helpful. So it seems like let me try and see that I understand correctly. It seems like whenever we want to delete some sort of node, we perform the deletion as if it was a binary search tree, right? And then once it's deleted, we take the guy that replaced it, who is now a duplicate, and we delete that guy. So all of the examples that we're going to see from now on are going to be related to leaves, because leaves are the only thing that can replace a to be deleted node. So that makes sense to me, although if I am saying this incorrectly and this is in fact not the way it's supposed to work, please let me know. Please let me know, because we will spend a long time and it would be frustrating to realize that that's actually not the way it works. I'm fairly confident though, given that all of the examples point to this fact. So great. Okay, so we were on example 5, if I remember correctly. Yes, delete 1 from figure 17. So we find 1, we delete it, it becomes double black. All right, let's do this ourselves. Double black, we see that its sibling is black and both of its children are black. So then we need to perform case 3. We remove the double black, so goodbye nil. We make the double black sibling red, 7 is red now. And if the double black's parent is black, we sort of pass it on to that. So now 5 is double black, 7 is red, and this nil will disappear in the next picture. Yes. And according to this, we have a sibling that's black, but both of its children are not black, so case 3 doesn't apply. The double black sibling is not red, so that doesn't apply either. Case 5 says double black sibling is black, yes. Double black sibling's child, which is far from double black, is black. So, whoa, what's going on? Okay, double black sibling is black, and double black sibling, yes, sibling's child. Which child? Well, the one that's far away from the double black is black. So the child that's far away from our double black is 40. And 40 is indeed black. So this does satisfy case 5. And the last condition is double black sibling's child, which is near to double black, is red. Okay, so it was engineered exactly for this case. Great. Now we have apply case 3. Yeah. Oh, sorry. Oh, this was explained in the previous step. Okay. So what do we do when that's the case? That's case 5. We swap the color of the sibling with the sibling's red child. So we swap them. This guy becomes black. This is red. Perform a rotation at the sibling node in direction opposite of the double black node. So now this is going to be black, this one red, and when we rotate to the right, which will make it so that 25 is the new parent, or the new guy, the new sibling. 25, 20 to its left, 30 to its right, 28 to the left, and 40 to the right. That seems to make sense, but let's see. Ooh, why is it so thick? Great. So we're gonna have 30 as the current guy, then 40 is over here, then here is 25. So let me 25. And then after that we have 20 and 28. So 20, and then we have 28. Good. So we swap the color of the sibling and its red child. So now 30 is going to be red and 25 is going to be black. So we have this 25 is black now, and 30 is the one that's going to be red. Great. 30. We swap their colors, then perform a rotation at the parent node in the direction of, perform a rotation at the sibling node in direction opposite of the double black node. So that would be, the direction opposite would be to the right. So this subtree, we need to rotate to the right. And the way that works is we make 25 the new parent, 30 sort of comes down, right? So we are sort of like rotating to the right. So 30 comes down, 25 moves up, so 25 over here, and 25 now has 30 as a child. Good. And now 30 inherits 28 as its new left child, and 20 travels up the tree. So this is what it should look like after we perform that rotation. And let's see. So yes, indeed, 25 black, 20 black, 30 red, 28 black, 40 black. Great. The last step is apply case 6. Oh my God. Okay. Because in that case, 25 is now the new parent, and the double black sibling, which would be 25, is black, and the double black sibling's far child is red. Yes. Okay, so now we swap the color of double black's parent with double black's sibling color. So 10 exchanges colors with 25, which leaves it the same. Now we perform a rotation at the parent in the direction of the double black. So now we need to rotate the whole tree to the left. Then we remove the double black sign and make the node normal black node. And then we change the color of double black siblings far red child to black. And so things should end up looking like this. We apply case 6, and everything ends like that. And voila, the red black tree is free of element 1 as well as of any double node. Life is good now. Okay. No words. Okay, conclusion. I have given examples and explained all the cases possible as one performs an elite operation on red-black tree. Without a doubt, it appears exhausting. Definitely true. But if you try these examples as many times as required, you'll understand the concept easily. Also, you can ask me a question on https://twitter.com/swatirashwal. This is great. This is great. We should follow this guy. I don't really have a Twitter account, so I cannot do that. But it's awesome. Pretty good article, and I think this is a good way to base our implementation on, sort of a good article to understand what's going on. So, okay, let's start coding now that we have a general idea on how things work. So you may be asking, Sharif, why did we start reading the article, right? Like, why couldn't we just code as we were reading, trying to fill out the cases? And the reason is most of these cases, as you can see, are very confusing sometimes. So coding while you try to understand is definitely not the move here. But we are doing it for a deeper reason. And it's that we need to see what we actually need in order to know how to design our code. As you can see, there was sort of like many cases, and cases where little pieces of code get reused. An example of that we saw yesterday with like our link function, right? Sort of linking to nodes. It's a piece of code that repeats everywhere and that we simply abstract it away and really simplifies our code. So I'll give you an example. Now we know that from our family members, we need to include a new one. Can you guess which one? So, of course, it's going to be the sibling, right? So we are going to include a function so that we can easily identify who the sibling of a given node is. So here I'm going to have this node, and I'm going to say, well, what do we want to return? Right? Great question. So what we're going to return is things really depend on whether or not is node left child, of whether or not we are a left child or a right child. Because if we are a left child, right, say I want to know the sibling of 3, which is a left child, we want to return the right child of our parent. And if we are a right child, we want to return the left child of our parent. So we're simply going to say, well, am I the left child? So from my parent, its left child, is it me? Right? If that's the case, then we're going to return the right child of our parent. Otherwise, we want to return the left child of our parent. Great. So now we have a sibling sort of function that allows us to extract the sibling of a node. What else have we seen that we need? We already have the code to perform the rotations. So now, fortunately, the only thing we need to do is we simply call write rotate, and then we get everything there. For the new viewers, hello. We are writing a memory allocator from scratch. The reason why we have red black trees on the screen right now rather than a memory allocator, it's because it's what we're going to be using as a data structure to manage our free blocks in the memory allocator. We have a problem, and it's the fact that I had never really interacted with red black trees before starting to code this memory allocator 2 days ago. So now we're implementing the red black tree data structure that we're going to be using. And we're sort of learning what it is, how it behaves. You may be saying there are thousands of red and black trees out in the internet, and you'd be correct. But when I say we're writing a memory allocator from scratch, we're doing it from scratch. Okay, so yeah, okay. We're now with the remove. It's the last piece we have. We finished insertion and find. And okay, that being said, let's continue. All right, so for remove, we know that what we have to do is we need to remove element as if in a binary search tree. Okay, and then whoever replaced us, right, is we perform the algorithm on whoever replaced us. Right? So as we saw before, in the examples that Swati has over here, we see that if you want to say delete 30, you first delete this as if it was a binary search tree. So 30 would have to be replaced by 38, right? But now there's a duplicate, right? 38 is now the guy that replaced us. And what we do is now, with the guy that replaced us, run that entire algorithm with this table that we have here. And the algorithm that this entire article tries to explain. It is very tedious, I do have to say, but it is the last thing we need to do. So let's push forward. Keep the morale high, people. Long night awaits. Because hopefully, I hope to not break this promise, but this stream will not finish until we finish remove. Yesterday, my goal was we won't finish until we finish insert. Then I upped the goal and saying we won't finish until we finish the entire red and black tree class, but that was not very possible given that remove is kind of difficult. And today, I hope to finish the entire red and black tree class, or at least sort of this remove method, which is the only one we have left. So to remove the element as in a binary search tree, we have to have something in mind, and it's that this is a bit of a particular red and black tree. The reason is that, as you can see, part of the instruction that Swati gives us is here. It's, where is it? I lost it. Okay, yeah. You first have to search for 30. Once found, perform binary search tree deletion. So usually in a binary search tree, when you want to delete something, you pass the key, right? And then what we do is we look for that key inside our tree, and then we everything is sunshine and rainbows. But notice that whenever the user wants to free a block of memory, they're not going to sort of give us a unique identifier of that block that we can use or search for in a red-black tree. Because a red-black tree is going to be identified by size. And the user doesn't give us the size of the block. They give us a pointer to the block. We can retrieve the size of the block from that pointer. The problem is that there could be many blocks of the same size. So searching for a block of a given size could return a block that we actually don't want to free. So it's very important, that distinction that we now have, that the user is actually telling us which node is the one we want to delete. That involves random access, which is the reason why we needed to, inside the document, the design document for how our memory sort of blocks will look like, we needed to include the parent. That's because we're going to perform random access. So we're not going to know who the parent is. The node has to tell us. So perfect. Given that, and having that in mind, we know that if we want to remove this element as if in a binary search tree, we simply would need to find sort of the minimum in the left subtree, or well, in the right subtree. Or if there is no such thing, I'm gonna hide this, or the max on left subtree. Right? So if we don't have a minimum in the right subtree, then we find the max on the left subtree. Yeah, and that sounds decently reasonable. Once we do that, we perform the algorithm of whoever replaced us. So now what we have to look for is we would have to somehow get, like, the successor, right? Successor. And that successor should be something like, we could have a successor function for a given node that just simply gives us the successor. I'm not sure how efficient that would be. Like, is it worth it to create a function that simply returns the successor of a given node? I would say that rather than that, it'd be better to create a function called minNode that, despite being the same as successor, it sort of has a more clear intent on what we want to do. We want to find the min node in the tree that starts at node. So let's do that, right? So that's a function that we now need to write. And apart from the successor, we also need the predecessor. And that's going to be the max node of the node's left tree. And here's the node's right tree, right? So let's write these two. They're going to be basically sort of images of each other. We have link, we have family members, we have data access, we have shape helpers. Is there maybe a category we can create? I think it could go under link. Link refers to sort of the transformation of the tree. So here we could code a sort of function that accepts a node and a node pointer to whatever the root is, which we're simply going to call node. And what we are going to do is we're just gonna like go all the way to the left, right? So simply, we're gonna create here this little guy where we say result. It's of course gonna be equal to a null pointer in the beginning, but oh yeah, we need to template this of course because nodes are templated by name_t, and we're gonna have that. Now result is equal to the null pointer. And all we do is while the current result is different from a null pointer, well, actually, results left child is different from a null pointer, we simply make result be equal to its left child. This is basically the way to say go all the way to the left, and then we return result. It's fairly simple piece of code, but it's also fairly simple conceptually. So we can simply abstract this away through the function, and that way we can just call it whenever we need to find the min on a given tree. The same behavior is what we're going to need on the right subtree. So we're just going to write another function that extracts the max node of a given tree starting at a given node. So we have this result is equal to null pointer. Great. And then while the result to the right is different from a null pointer, then we want to say result is equal to the result that goes to the right, and then we're going to return result. So that should work. Hopefully it works. And let's add some sort of oxygen comments to this. I'll just include a brief or sort of returns. Let's see. Smallest node in tree starting at node. And then we're just going to copy the exact same description for max node. Okay. Feel that's good enough. I don't want to spend much time in the oxygen. It's just biggest node in tree starting at that. Okay, perfect. We put our mouse over it. We should be seeing the documentation show up. Yeah, returns the smallest node. Perfect. Now we're gonna go back here to remove, and we have that, right? So successor and predecessor. And what we're going to want to do is we're gonna want to replace our current node with whatever we found. So I assume from what we read that we simply change its data, but let me make sure that that's the case. Deletion in a red-black tree is a bit tricky than other binary trees. Here I present the delete operation with suitable examples to demonstrate all the cases. You should have some knowledge of all operations performed on a binary search tree, an insert operation in a red-black tree. You should be familiar with terms like sim and parent. Yes. Yes, we know this already. No deletion cases. Okay. Skip this table. Okay, we're back to where we were. First have to search for 30. Once found, perform BST deletions. Okay. There is a decision that we are faced with, especially when it comes to our memory allocator. And it's the fact that whenever we say in this case, right, I'm going to take this tree as an example. Whenever we want to delete 30, right, because I don't know, it's no longer free, we need to move 38 up the tree. And what that means is we cannot just change that in the tree itself. Sort of like, it's not like I can just change the value of this node, because once again, every node should represent a block in memory. And this value is just the size of the block. So if we are to just change the size, nothing really changes. It's not like magically changing the size changes the amount of memory that's available. We actually need to like put the node object in its place, like quite literally that node object, specifically that one. So yeah, I think instead what we're going to want to do is when it comes to replacing, we need to just put the entire node rather than migrating only the key, which is a little bit tricky, if you ask me. But okay, we have the successor, we have the predecessor. So now what we have to do is we need to replace the node with whoever this guy is. So in the case of a successor, we're gonna have, I think I'm gonna come this line. How do we replace an entire node with another entire node? That's a great question. Because we simply would need, like, you know, the node's parent. Now it's whether the node is a left or right child. We need to replace it. We need to make it point to the successor, right? So whether it's a left or right, I don't know which one it is. We need to make it be the successor. Now the successor's parent, so successor parent needs to be equal to that node's parent. And not only that, but the successor now needs to inherit the same children. So to the left, it needs to have the same children and the same stuff. So yeah, this seems like a little bit complicated, although we can leverage the functions we have built up until this point in order to make this easy. So what we want to do is we want to link the current node's parent. We want to link it with the successor. Where do we want to link it? On the left or the right? And the only way to tell is whether by determining whether or not node is a left child. So is the node's parent, is its left child equal to myself? If so, then yes, I'm a right child. Otherwise, no, yes, I'm a left child. Otherwise, no, I'm a right child. And that is what we're going to feed to the function here, where true means left, so link them on the left, and false means link them on the right. So we have linked the parent and the child in sort of the new node that's gonna be taking place. Then we need to link the successor as the new parent of the node's left child. And of course, we're gonna want this to be a left relationship. And now we're gonna wanna link the successor with the node's right child. Gonna be false. False corresponding to right. So now node right is gonna be the successor of that guy. And then we can simply get rid of node. So get rid of node, and that means sort of freeing node. And in the case of C++, that would be just delete it, right? So yeah, I think this is the code that we're gonna need just to replace sort of the to delete node. Great. So yeah, it's sort of like what's the name of see, I'm not a native English speaker, so I struggle sometimes with some words, but what's the word of, you know, when you have like a king, right, and that king has like children, what is the name of the role of the children in this case? Like prince, but no, it's like the children will in the future become king. Oh, I think it's heir. An individual legally entitled to receive the property, assets, or title of another person upon their death. Yes, perfect. So that's a perfect name for a variable. The heir. Do you pronounce it heir or hair or? English is weird sometimes, so I have no idea. Let's see.
Heir.
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 Heir. Okay, so heir. We're gonna name this variable the heir, and we're gonna make it right. If the successor is available, then a successor, and if not, the predecessor. So the reason why we do this is you can imagine that at some point in time, we could encounter a situation where we have something like this, say 25, right? Then I have, say, I don't know, 15, and then I have 20, where our code, if it only looks for the successor, as we have coded it up until this point, then once it detects that there's no successor, right? Because right here, there's no successor. Once it detects there's no successor, it's going to be like, oh, there's no successor, so I can just simply remove this guy. But that's not the case, right? The left subtree still needs to have a new parent. So that's why, even though it's possible that sometimes we don't have a successor, the predecessor needs to take its place. So if we have a successor, then grab the successor, otherwise the predecessor, and perform this entire algorithm with the heir in mind. And that's what this if in the comment was pointed at. Like, if we don't have a successor, then whatever. But I feel this is a much cleaner way to do it. Great. So now we replace the toDelete node with the heir now. The problem with that is that we are not going to be able to... We've entered a tricky situation because, as you can see on this red-black tree, the heir is sort of taking the place of the node that's to be deleted, right? So, like in the example that we have on the right, I'm just not going to care about colors for now because this is sort of the very start of everything. If we have 30, then we have 40, then we have 25, and then we have 38. Notice that what our code is doing currently is it's literally grabbing this node and taking it up here and replacing the old one. And the problem with that is that now we don't know where to put the double black, right? Because like we have forgotten about this position. So we need to store a reference to sort of like, you know, to that guy, right? What is the thing that I need to mark as double black? And I think that's going to be the task of Of who? Great question. I don't know. I think we just store a position to the heir's parent. And then once we are done with the heir, we know that heir parent is equal to the heir's parent. And the reason why we store this is because we're going to be messing up with the heir all over the place since we're linking it with a bunch of other stuff. So once we're done with it, it's going to be like complete hell to try and find it. Let me think. Because not only that is the thing we need, we also need to know whether or not the heir was the left or right child of its parent. And so now we need to say, was heir left child? And then we're going to include sort of the code necessary to determine that, which is actually very easy, right? Heir parents left is equal to the heir. Then I know that, yes, this was the left child, otherwise false, this was not the right child. But this was not the left child, right? But this, you know, like, do you smell that? Because I smell it, right? That is the smell of disorganized code. This does not smell well, right? Like, the fact that we need to store sort of the heir parent and whether or not the heir was a left child, it seems like a little bit of a sign that this can be done in a simpler way. Like, we could definitely proceed with something like this. I'm just saying that it's fishy. It's suspicious. Like, this thing does not really look good. And it feels more like a patch rather than actual code we would want to write. So, let's think about it. Let's think about it. And pum. Because so what I'm saying is this, right? Like, here we perform all of these links and all of this stuff to sort of conciliate the fact that we're moving this node, this 38, and we're making it replace the 30. In our memory allocator, we cannot just change the values. We like, the node itself is the value. So it's not like we can just change that 30 for a 38. We need to change all of 38's connections to match whatever 30 was connected to before. But in that process, we forget about where 38 was located. And that's why I'm saying, like, oh, let's store the heir parent and whatnot. Is there a way to sort of get rid of that need of storing the heir parent? I think the answer is no. So it's gonna be a bit of a difficult thing to figure out. Well, not a difficult thing to figure out. I think, okay, as much as this hurts me a little, I think we're gonna have to proceed with it. I think we're gonna have to, to go forward. Okay, that's completely fine. So now we replace the toDelete node with its heir, and after that, what we need to do is we need to make the position that the air was occupying, we now need to make it a nil double black. So when we link stuff like this, right? Oh shoot, no, 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 no. When we link stuff, just like we're doing here, uh, all of the links that belonged to that previous guy, to the guy that we're modifying, are lost, right? So right now, 40 does have a left child, and that left child is a nil. A design decision that we have to commit to is how do we represent double black? It's a bit weird, I would say. How do we represent double black? Because in our memory allocator, as I've been saying, we're gonna have a sort of space for the color, but it's only gonna be one bit. So we can only store red or black. We could make this 2 bits or increase the size of it, sure. But it may not be, I don't think it is ideal. So if we can find a different way to represent what a double black looks like, or how we represent a double black, that'd be great. That would be absolutely amazing. Let's do this. Let's have a compromise. I need to do my laundry now, so I just need to put my clothes in the washer. And after I'm done with that, I'll think about it in the 2 to 3 minutes it takes me to take the clothes to the washer, and then I'll come back. Okay? That's a compromise. We'll be back in a few seconds. Don't worry. again. Hello, hello, hello. I'm trying to see if the sound is being captured. Yes. Hi. Whee! Yeah. Okay. Perfect. Um. Welcome back. Yeah. Well, I guess not welcome back. You guys have been here, but I'm back. And okay. So the clothes are now in the washing machine. Now we're gonna have to wait. And what have we thought of up until this point? If anyone has an idea, please let me know in the chat. But currently, what I'm thinking of is two things. We can actually sacrifice another bit just to store that inside the node. But I feel that would be a little bit unnecessary. I propose an alternative. And it's the fact that it seems from what we have already analyzed from redback trees and like after reading this entire article related to deletion, we're only going to have one double black at a time, right? There's no point in time where we have two double blacks. That means that we can simply store a variable of sorts that's called just double black, right? That tells us like whether or not a given node is double black, or we can simply have the double black node have this distinctive name so that we can keep track of it. I feel that's a reasonable approach. It doesn't increase our memory consumption, especially when it comes to sort of like storage in our memory blocks. Nothing like that. So I think it's completely perfect, like in the sense that we can deal with it. So yeah, okay. So we know how to represent double black. I'm gonna proceed with that. If anybody wants to oppose to it, let me know. Okay. So now 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 I want to let's see. Let's proceed and see what it is that we have to do. Okay, the resulting red black tree will be like 1 in figure 4. Element 30 is deleted and the value is successfully replaced by 38, but now there's a duplicate. Since the node with element 38 is the red leaf node, remove it. Okay, so we have the first of cases, right? So that'd be like case 0. If sort of the air is red leaf, then just remove it. And what that simply means is we do nothing. So we return. Right, because the air has already moved away from here. There's nothing else we have to do, so we return. But that's only when the air was what's the name? Air's color, which we access through color air, is equal to red. Then we want to return out of here. So great. Okay. The question is, well, that's not really always the case, because although the air could be red, the parent could be black. Oh, and in that case, we could be just straight up violating the red-black tree third property, which says that all paths from a node to its nil descendants contain the same number of black nodes. So it cannot be as simple as that, although that's exactly what the guide is saying. You first have to search for 30. Once found, perform BST deletion. For a node with value 30, find either the maximum of the left subtree or the minimum of the right subtree and replace 30 with that value. This is BST deletion in short. And the resulting red-black tree will be like 1 in figure 4. Yes, element 30 is now deleted and replaced by 38. But now the task is to delete the duplicate element 38. Go to the table above and you'll observe case 1 is satisfied by this tree. Oh, so never mind. The table still applies. So if node to be deleted is a red leaf node. Hello? If node to be deleted is a red leaf node. So, oh, okay. I understand. So BST binary search deletion assumes simply changing the sort of contents, which means that if this was black, it would still be black, right? We just keep its value of black, which says a lot about the fact that we completely missed that when we were writing our code here. The as color has to be equal to the previous owner, right? So in this case, node's color. There you go. So after that, we can definitely say this, although we have to be very careful because it's not as simple as that. I think, okay, this is what I'm talking about, because now we need to store an extra variable to store as OG color, right? And so now we have like, we're slowly but surely creating a bunch of patches that just don't, that just doesn't feel right. It seems necessary for now, but not sure. Let's see. If the air's original color is red, then simply return, right? We already swapped it with the guy we needed to swap it with. And since we're swapping the entire node, we also sort of unlink it from 40 and it's no longer here. So we just simply return. And that is case 1, right? Case 1. Let's put this as case 1. Hello? Yeah, perfect. Search for 30, yeah. So we deleted into the above table. Since now with element 38 is a red leaf node, remove it in the tree looks like the one in figure 5. So that if you perform correct actions, the tree will still hold all the properties of the red-black tree. Great. So what this assumes is from now on, first we perform binary search tree deletion, and after that we focus on the deletion of the air, right? So let's see. To delete 15 from the red-black tree in figure 16. So it is interesting because all of our problems are always going to start with a double black nil, right? So since the nil is double black, we can So what is it that I'm complaining about? Well, I'm complaining about the fact that this is a nil child, which means that it's represented as a null pointer. But if you have something be a null pointer, it's not like you can attach data members to it. You cannot say sort of like, node, is it double black? Because it's just a null pointer. So we somehow need to keep track of the sort of double black information without referring to this node. So we have to keep it externally, which means that whenever we want to talk about this node, we need to refer to the heir parent and the was heir left child to know what we're talking about, to know that the parent is this and that it was its left child, and then we know where that null pointer was located and what it is, what thing is the one that's supposed to be a double black. So, and that doesn't really convince me. So let me think. Let me see if there's a way in which we could change the way things are. 20 nil 30. 10, 5, 20 nil 30. Nil. Ugh. Is there a way in which we can change things around? Difficult question. Because nil is double black. Sure. And then, like, when we have that double black, it is the literal most important piece or node in the tree at that point in time because everything revolves around it, right? Like, its sibling, its child, whatever. So, I think what I'm going to do, and this is going to be a little bit controversial perhaps, is I'm going to create a ghost node. So some guy to which we're just going to call double black, right, DB, and this random guy is just going to represent the node that we want. We don't even need to give it a sort of value. We can just default initialize it with whatever this has. And we can, after that, link it with the old parent. So link heir parent with this new guy and link it on the direction in which the heir was a child of the heir parent. So what I'm sort of doing is in the example on the right, let me erase this. We are creating this like 10, right? Then 20, good. Then 30. I'm not really caring about colors right now. And 5. And then I'm just inserting some random ghost node. 0, right? And this guy, he's just there, right? Like for now, we're just gonna have him there. And it's going to represent precisely that double black node. That's why the only way we have to refer to it is double black, right? So great. I think this way we can keep track of all the things sort of that we are doing. Yeah, I think that's fair to assume. That's fair to know. And I just want to make it so that its color can just be specified here, where instead of red, it's just going to be the color of the original air. The air's OG color. Perfect. And then after that, we're going to say, well, if the double black is actually red, so double black being the guy that's like, the guy with just the leader or the victim, then this is going to happen. The entire problem is now drilled down to get rid of this bad boy, double black, via some actions. So now we simply need to implement the cases, right? So case 2 is something like this. So if the double black node is equal to the root of the tree, then there's something we need to do, right? That something is, well, first of all, let me check that this access that we're performing for the double black being the root is actually correct. Because suppose that we have a tree that only has a node, right? Then how would we detect whether or not this is the root? Like its successor is the root itself, predecessor is the root itself, then the heir is equal to either of these, the heir parent. Okay, and then that would lead to some sort of interesting. Okay, so in min node, one thing I forgot to the check for is, of course, if the node is a null pointer, then we simply return you don't have any sort of minimal thing over there. And in max node, if the node that you pass me is a null pointer, then you also have nothing to see here, right? And so what that's going to generate is the problem that what happens if both successor and predecessor are null pointers, and in that case, we simply remove the root, right? We sort of have, yeah, everything the way it's supposed to be. So if the air is a null pointer, then all we need to do is we need to say, well, delete the root, and just to not leave a dangling pointer, make the thing that start is pointing to, which should be its right child, I want to say. What does root access? Root, yeah, there you go. It accesses the start right. Okay. So we can just use that, and we can say delete the root and make root be equal to no pointer. Right? And so that way we simply return, and that's all we need to do. So that's in the case if deleting the only node left, then we're going to do this. Now with this air parent, and then this was air children, and the air's original color, and all of that, we can basically sort of save ourselves the trouble. We don't really need an extra variable. We simply need to create this earlier. So node t star of double black, it's just going to be equal to this thing. So we just initialize it with the color of the air. And then here we can simply delete this. Then what we're going to do is we're going to find whether or not the node is the left children. Then we link them together, blah, 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 blah. Yeah. Is there perhaps a better solution? Because right now, so right now, look at our code right now, right? We have like all of these patches, has air, was air, this double black here that needs to be initialized here, but actually we are going to change the way the air works. And so now we have to link it against a different sort of set of parents. And like, this is, I feel there's a simpler way, right? And I want to think about that simpler way. So give me 1 minute. Moving through the language is going to be good enough. And then after that, we're not going to have a problem. And then we're going to be completely fine. Sure, that's cool. And then we keep the references. And after the color, the color needs to stay the same and everything else. Okay, I think I have a solution. I think we can improve this by developing a helper that rather than data access or a family member, it's a tree modification, right? So over here, I think that would be a great title for this section because I didn't know how to name it. These are family members, this data access, that's shape. And this is tree modifications, right? So tree modifications. Included is link, And min node and max node, they're not really sort of, tree modifications. So I think maybe I'll just include them in data access for now. I just include like to do on appropriate section for these guys. Then I'll just point it down like for these guys. Great. So what we're going to do is we're going to write a function, a helper, int, that is going to be called swap. And what swap is going to do is it's just going to accept a node A, or sort of A, and then it's going to accept another node called B. And the only thing it's going to do is it's going to swap them, right? Oh, wait. Hello. Oh, we have another person. We'll have a person in the chat. Gaurav Mali. Hi. welcome to the stream. It says I'm lagging a little. Oh man, I'm really sorry. Wait. That shouldn't be happening right now. I tried to set up the stream so that this wouldn't happen. It seems like it's a little bit more stable now. I am so sorry. I hadn't seen your message. I I was perhaps too embedded into the code. But welcome to the stream. I'm glad you're hanging around. Currently, as the title says, we're writing a memory allocator from scratch. This is not the memory allocator itself. We're working on red-black trees, and that's because that's what we're using as a data structure to store all the free blocks inside our memory allocator. The reason why we're implementing red and black trees from scratch is because it's a memory allocator from scratch. So I really want it to be from scratch. And not only that, but I wasn't familiar with the concept of red-black trees. I've used AVL trees my entire life instead. So you gotta get familiar with that to know how it will interact with the memory allocator. So that's exactly what we're doing, and that's why sort of we are focusing on this class. Our first day of stream, we actually implemented sort of the design for a memory allocator. And we also, now in the second day, created sort of this insert function for our red-black tree, verified that it worked with some tests, and we created the find function for our red-black tree. Now we are in the process of implementing remove. So it is a little bit of a pain, but we're starting to sort of figure out how to do that, right? How to come around the little bit of a complicated part that we have with delete over here. So yeah, have you enjoyed the stream? Feel free to leave the stream. Feel free to come back in. I'm honestly just going to be here, and I won't finish until we have finalized the remove function. And yeah, that's all. That's all. So thank you for hanging around. You should, talk in the chat, ask any questions if you want, propose any ideas. If you consider the code is messy or there's something that should be changed, then let me know. But yeah, so we're gonna swap. We're implementing here this swap function where it's just gonna swap two nodes, sort of the position of two nodes. And the way we want to do that is, let's see. Well, first, I want to change, the parent of these two guys. So I feel like we can simply use C++ as swap, right? The standard library swap, where we can just say swap A with, sorry, not A with B, but rather A's parent needs to be swapped with B's parent. So I'm gonna have a little drawing here on the side. Because we need to keep track of. Usually, when we work with trees, it's like not an easy thing to do. So, sorry, my mouse. It's It has like a little rock somewhere. So it's like scratching my desk. And it sounds like a little bit annoying. Oh, there you go, it's gone. All right. So we are going to have this thing over here. Let me check how the stream is doing. Oh, great. Okay, it's working. All right. All right. Hold to your seats because right now what we have is this. We have like, there's gonna be a huge tree structure, and then here we have A. Then we have some random node, some other random node, and then maybe there's B over here. And then B is also gonna have children, right? B is gonna have a child here, right? And what we are doing is the following. We're gonna swap A's parent with B's parent. So now this guy, it's going to be pointing to A, and this guy is now going to be pointing to B. Right? Or I guess it's the opposite way, right? The opposite way in the sense that A points to this guy, and A is aware that that's its parent, and B is aware that that's its parent. But we have not yet notified each of them that their children have changed. So what we have to do is we need to sort of change these two, right? And so we're we're gonna have to say sort of like A's parent. So I guess Bo is a left child, right? Is A left child, and that we can determine easily by simply saying, well, my parent's left child, is it me? If so, then true, otherwise false. And the same thing goes for B. Is B a left child? Well, this would just be that B's parent, its left child, is B itself. If that happens to be the case, then yes, it's true that B is a left child, otherwise it's false. And so now not only do we swap the parents, but we also sort of get this guy to be something else. So A's parent to the left, right, is now going, or I guess, if is a left child, if A is a left child, then we need to modify the left child of A's parent to now point to B. Otherwise, we need to modify A's parent's right child to now point to B. And we repeat the same thought process, but this time with B's parent. So if B is a left child, then we need to change its parent's left child to point to A. And similarly, in the opposite case, we need B's parent's right child to point to A. And now we simply swap the parents between the two. So this is sort of the parent exchange. There you go. And now what we need to do is we need to swap the children, right? So this will be like the children exchange. And the way we're going to achieve that is fairly simple, I would say. Like, we can simply std swap A's left child with B's left child. But be careful, because the left child now needs to know that its parent has changed. So A's left child, right? If it exists, because remember that it could have a child a null pointer, then we're going to tell that left child that its parent has now changed and it is no longer A, it's B. And similarly, if B has a left child, then we need to tell that left child that its parent is now A. Good. I mean, I feel that that makes some sense. And now we need to do the same thing. So this is the left child. We need to do the same thing, but for the right child. The right child. Child. It's that if a sort of its left child, no, sorry, its right child. I think we can just copy this code, right? It's the exact same thing. And now that we have this, we can simply change this to right. Perfect. Hello to the new people that are joining the stream. Welcome. So currently we're writing a memory allocator from scratch, and you may be saying, Sharif, but the thing you have here is not a memory allocator. This is actually a red-black tree. We are working on red-black trees. And the reason for that is that we have decided for red-black trees to be the underlying data structure to support and store the free blocks that we're going to have in our memory allocator. And that requires, as I said, we're going to code the memory allocator from scratch. So that means we're also coding the red and black tree from scratch. And also, the reason why we're doing the red black tree is because I'm not very familiar with red black trees. I've used AVL trees my entire life. So now is the time to learn about them so that we can also consider sort of how we are going to embed them into our memory allocator. So yeah, I mean that's basically it, and we are currently working on the removal process on the red black tree. So yeah, thank you for hanging around. Feel free to get in and out of the stream however you want. If you're busy or something like that, I am going to be here because I'm not going to finish the stream until we finish. I've been streaming for around 2 hours now, so it'll be a long journey. Right now, we're writing this function that swaps two nodes. And okay, we exchange the parent, right? We exchange the parents, we exchange the children, and we also, yeah, so the left child we are able to exchange, and the right child we're able to exchange. All right, so that's great. And not only that, but we are going to I think this is all for the swap function. I think this completely swaps the two nodes. This makes it so that A now exactly occupies B's place in the original tree that didn't have all of these arrows. And B now gets to have the privilege to move to A's place. I think this gets rid of any sort of conflict we could have in between the two. Yeah, I feel that's all. That's all, question mark? Yeah, okay. So we have swap, and with swap, now that we go back to the remove function, we can definitely simplify this code a lot. Because the only thing we need to do is, rather than storing the heir parent, bye-bye, rather than storing whether or not it was a left child, bye-bye, whether or not storing the double black, bye-bye, right? What we're going to do is we simply say, well, swap the two of them. So swap, sorry, not std swap, but our swap. Swap the two of them. So swap my node that I want to delete with its heir. And now I'm gonna know that the heir is the new thing that's just gonna occupy the new place. That's the heir. And the node now passes to be the thing that we want to delete, right? And this way, we can simply make it so that air has, so the color of color of air is equal to the node's color. Yeah, because the pointers sort of stay the same. We don't change the color when we do the swap, but we do want the air to have the same color as the node and vice versa. So I think that rather than doing this, I think we can just use cd swap on the node's color, and the air's color, right? So not only do we swap their things and like all of that, we also need the nodes. So this node we no longer care about, and I think, yeah, he's already gonna be deleted. So I think that's the way we can do this. And look at how beautiful this is, because now it means that we can just get rid of this entire wall of text. And we can also get rid of this. See, that's exactly what I was meaning when I mentioned that sometimes there is this sort of sense in which the code starts feeling fishy, where it's like suspicious, where it looks like you're just patching your code rather than actually thinking about the design. This is exactly what I meant. Like if you now look at this compared to the huge wall of text we had before we implemented swap, with all of this like air parent and whether or not the air was like correct, like, right? Like look at this. Look at this wall of text. Look at this wall of code. It's difficult to understand. But if you switched it, if you really think about the design and what we really have to do, you arrive at this notion, right? All of those lines replaced by these two. Swap the two, swap their colors, and now node is the evil one and air is the one that gets to stay. Isn't that beautiful? Like honestly, in my opinion, that's like pretty cool, right? Like when you think hard enough, it is not only or sort of yourself, you are not the only sort of referee on whether or not the code is working well. The organization and structure, and I don't want to say it, but like beauty of the code, which is kind of relative, but the beauty of the code is also a referee when it comes to that. It tells you, do you have sort of the right model? Are we thinking about things correctly? And the more readable it is, the clearer the picture you can paint. And really like that about sort of that little nifty optimization that we made. So now, Node is the evil guy, right? We agree on that. Node is the one that's going to be sort of at the bottom of the tree, and that we now need to put, like, sort of, this is now our next target for deletion. No, this is the guy that we switched, and now he's at the leaf, and this is the guy that's going to be the double black in our red-black tree. So case one tells us that if the node is a red leaf, then we just remove it. So that's exactly what we're doing. If node is red, then all I'm going to do is I'm going to delete node and return. I just get rid of him. Not only that, but we sort of need to sort of like, actually remove it, because when we performed the swap, this node is going to be connected to all of the heirs, sort of parent and children and whatnot. So we also need to take care of that. And I think the way we do that is um, um What a great question. So I feel we could just simply call remove and then call it with the node, right? Sort of a recursive call saying like, bye bye, it's your time to go. But that doesn't seem right because of the way we're handling things here. We would find ourselves to be there and then nothing would really change. We could include a case where we simply have that sort of like, if this thing is a leaf, then we're going to proceed with the cases. Otherwise, if it's not, then we wanted to sort of have all of this code sort of indented, right? But I feel that's just not good, right? it just doesn't look great. And so let's just not do that. I think we can simply say like, please tell your parent yeah. Well, I think the way I'm gonna express this is we're just gonna have to fix this BS because this just makes right. This thing is gonna look ugly, but we need to know whether or not the node is a left child. This we have done like countless times. So we simply say, well, is the node actually? Why have I been writing all of these? Yeah, these guys, all these true false. Like we can just simply write this. I don't know why I was. Why was I writing it that way? True? No. Also false? No. Okay. Interesting. Well, I don't know why I was writing it that way. But if the node parent, if my parent's left child is me, then that means that I am a left child. So if I am a left child, then what I'm going to do is I'm going to grab the parent and then its left, make it a null pointer. Otherwise, we're going to grab the node and then its parent, and we're going to grab its right, and we're going to make it a null pointer, right? And after that happens, we are just going to consider that a removal, right? Because the only reason why we did this is like to tell the parent we're gone, right? And once that's done, we simply delete ourselves and return. Right? That's the way so if a node is a red leaf, we just remove it. And we need to fix this BS because this looks like something like this would be desirable. All of the extra stuff we're doing, I'm pretty sure we could somehow find a way to skip or at least to simplify. It is not difficult to understand, so I would have no problem leaving it there, but if we can improve it, it's better. The next case, and for this, I think we're gonna have to recur or like go to the table that we have here from Swati. And Swati, with this very nice table, tells us sort of like how things should be done. If we have the double black being the root, so node is now considered to be our double black, right? So if a node, because he's the evil one, right? He's the double black. So if the node is the root, then we need to remove the double black and root node becomes black. So interesting. Ooh, so what happens, say for example, if we have a red-black tree where the only thing you have is the root, right? The root is black. So when we apply deletion, we would need to account sort of for that case. Oh, there you go. If deleting the only node left, then we do this. Perfect. All right. Case two. Case two. So if the node that we want to delete, or like, sorry, not node that we want to delete, but the double black node is the root. I feel that's something important to note. So here, right? Node is now thought of as double black, right? If the double black is the root, then we remove the double black and root node becomes black. So we simply make sure that the root's color is black. And since we are not keeping track of double black in any sort of weird sense, or like storing it anywhere, we're just keeping track of it implicitly by knowing that node is the variable with double black. We just have nothing to do. So return. There's something that I do have to say, and is that well, actually we can return here. This is fine, because if we're at the root, then everything's great. Case 3 is going to be a little bit more involved, where we have, well, if the sibling of my double black node is black, so if the color of my sibling is black, and not only that, but both of its children are black, so the color of my sibling, so I think we're gonna have to sort of expand this below the if. So not only that, but and the color of my siblings' children. So my sibling, its left child, is also black. And the color of my siblings, okay, my siblings' node, its right child is also black. Then we're going to, let me see, am I lagging? No, okay, that's perfect. Then we're going to have to continue, right? This is sort of perform the action that we were thinking of. Not sure if that alignment is the best, but I'm gonna run with it. I'll fix the alignment later because I don't like to have this like that. It's okay. Then we need to perform a couple of things. So we remove the double black. That means if no double black, then delete the node. So that would mean, okay, we simply just get rid of it, I suppose. So here we remove the double black, the marker. Then we make our sibling red. And then after that, if parent is black, okay, if parent black, then make it double black. Otherwise, make it black. Right? So notice that the removal of our double black, I think, should be last, mainly because we still want to keep a reference to what the node is, and all of that, especially when we have like a null node. We make our sibling red, and that's fairly simple. We simply say sibling node, and then we grab its color attribute, and we say you're now red. Great. Now, if your parent is black, make it double black. So if the parent of our node is its color is black, it's black, then we want to make it double black. So what that would mean, it's like, make it double black. whatever that means. In this case, it would mean sort of node being equal to the parent. So now the parent is the infected child, right? It's like the bad child. The reason why we shouldn't be doing this, or like at least not take it so liberally, it's because we still need to remove the double black. So that means that at some point in time, we want to do something like this whenever our node is a nil node. Or we want to be, or we want to just not do anything in the case that's that guy was not the actual thing. So yeah, we need to sort of consider. I'm just gonna add a warning instead of here, and like a little exclamation mark. Now we're gonna say if the parent is black, then we're gonna make it a double black. Otherwise, make it black. So if the parent is black, then we make it a double black. Otherwise, else we just simply say, well, no parent, and your color is now equal to black. Let's wait for the C++ extension to color everything, see if there are no errors, and I think there are none. So I think we can consider ourselves as done with that line. And then when it comes to remove the double black, we have a bit of a situation, because when the node is like a good node, right? When this is a node that's double black, but not because it was involved in the initial deletion process, instead because it was just infected, then we simply need to do nothing, right? Because we're keeping track of double black implicitly through whatever the node variable points to. We know that guy is the double black. But if it is a nil node, then we need to actually remove it. So somehow we're going to have to figure out a way to keep track of whether or not it's a nil node. It's a nil node, and by a nil node, what we mean is it was involved in the initial deletion process. So if it's a nil node, our little guy, then the only thing we want to do is perform the same thing as case one, where we sort of just delete him, have a face. Otherwise, we just don't do anything, right? So there's a couple of things that we need to answer here. First of all, sort of how are we keeping track of... So we have these two questions, right? How do we make this double black without forgetting who the node that we need to erase is? And how do we determine whether or not the node that we want to erase is a nil node? I don't know. We're gonna have to think about it. I'm not sure what else to say, but that is the truth. We have to really think about it kind of hard. So there's also something that I've been implicitly coding up, right? And that's the fact that currently, right, as it stands, we're sort of, or at least the way I'm coding this, is I'm transmitting the double black infection up the tree. So what that means is that whenever somebody is infected with double black, we sort of make that be whatever node points to. So what that means is that we're going to recursively solve all of the problems until we get to the root of the tree, and only then will we know there are no more problems. That means that all of these cases need to be evaluated every single time until we reach the root. So it's going to, all of this is going to have to be enclosed in some sort of a loop, right? Some sort of while that tells us, okay, while you're at it, right? Keep going. and do so until something. That something, up until this point, seems to me that it's that until the node is equal to the root. The problem is that if this is to be the case, or like while the node is different from the root, if this is to be the case, it means that whenever the node is the root, then it's going to get out of the while. But notice that case 2 refers to the case where the node is the root, so we cannot have this as our condition. I think that what we could do is we can just have this be a while true. And hear me out. I know what you're thinking. This looks really bad. While true, right? Like why are you putting that? I agree. Controversial decision. But eventually we know that we're going to reach the root. So we know that we will eventually reach case 2 and that we're going to return. Or rather than return, let's apply break, right? Because I don't know if I want to include something after this loop. I don't think so. Either works, but let's just apply break for now. So what that's going to do is, as I said, when the double black infection infects sort of the next node in the tree, the while loop is going to run again and treat that node now. So that's why we think of node as the double black guy. This way we save the recursion aspect of it, which it's not that recursion is bad, but it's definitely something that we can save on when it comes to the memory allocator, and we don't need to use the memory that a stack frame consumes, although it's negligible. It's good. It's also, in my opinion, a little bit more understandable this way, because we know that we are always moving upwards, so we don't really have to call some sort of recursive routine, because it's not like we can call remove on the double black node, because we will be passing to remove a malformed red black tree, and that's just not a thing we do here. And not only that, but it would erase the double black node, which we don't want that to happen. So let's see. If color of the node parent, make it double black. And the way to make it double black is to add this implicit sort of conversion. And the question is, okay, how do we detect this is a nil node? So in this situation, I'm feeling compelled to Oh, you give me a few minutes. Okay, there we go. If it is a nil node, yeah, but this function just doesn't exist, right? This is pseudocode. So how do we detect whether the node we want to delete is a nil node? I'm willing to say the way we can detect that, and I'm not sure if this applies to every single case, is whether or not it has children. So if both of its children are null pointers, then it means that it's a leaf. But the only way we could have arrived at wanting to delete a leaf is if that was the original thing that we were working with. So that is the original nil node. I'm sure there could be some problems, especially like the only thing that makes me doubt about that is case. Sorry, case 5 and case 6. Sorry, I'm yawning because it's 9 p.m. where I am at. I'm on PST time, so yeah, 5 and 6. make me doubt about this, because when we perform the rotation, it could just so happen that the thing that's infected as double black gets like sort of moved, and now it's not gonna have any children, but this was not the original guy that we wanted to remove, right? It is now instead, it just has no children just by coincidence. So let me see if whenever we perform a rotation, it is the case that we can guarantee that whatever ends up with no children is not going to be a double black node. So, boom, boom. Let's see. If the black sibling is red, perform a rotation of the parent node in direction of the DB node. So if it's in direction of the double black node, we're saved, right? Because that means sunshine and rainbows. Because the double black node is still going to have no children, so we can still identify it by that. Here, when we perform a rotation at the sibling node, then there's no problem with that because the sibling node has no involvement with the double black node. And so that transformation will just not touch the double black node. And here, 6 seems to be dangerous. Perform a rotation at double black's parent in direction of the double black. But no, that's still fine. Because if it's in the direction of the double black, then it means that double black is still going to be a leaf. It's still going to be bad. So yeah, we cannot, that is sort of a good conclusion. We cannot end up with a double black that is a leaf and was not the first double black to ever exist. So with that conclusion in mind, we can simply say if the double black has no child, right? If its left is equal to null pointer, and its right equals to null pointer, then we delete him. And by deleting him, we need to add this part that's like currently BS, but it's okay. There you go. So I think that's case 3. And okay, there's something that there's something I'm concerned about. And it's the fact that you could have this situation where I'm trying to think if that's possible. Where you have something like, say we're in this tree, right? And then we have this guy over here, say 40. I don't know why it's so thick. 40, right? And whenever we have this 40, let me write that a little bit more thin. 40. And whenever we have this 40, we encounter the problem that if this is double black, then we say, yes, this is a nil node or whatever. And then maybe for some sort of reason, the double black gets transferred to the parent, just like what we have here, right? If the color of the parent is black, then make it a double black. And then we delete 40. Then 30 is going to have no children. But it wasn't the original double black. So is that a problem? The reason is I think that is a huge problem. It's yeah. Yeah. So I have to be honest with you guys. I don't know how to get. I need to think a little bit more before I proceed because it's currently not clear to me how we can perform this cleanly. We can do it with like patches and stuff, but I'm trying to find a clean way. Um, Clean in the sense of both performance and readability of this. Although performance at this point is not at all affected. This is just pointer manipulation. Remove the double black. So how do we know whether or not we need to remove that node? Well, we all ever gonna end up in a situation like that. We have two things. I'm pretty sure, yes. And so after that, yeah, we're gonna have to want to remove it, but we're not going to be able to because we don't know whether or not this is a nil node. Honestly, if I'm being completely sincere with you guys, I think if we just add a flag that says is db nil, right? Initially, it's going to be true because we're going to be working from the leaves up to the root. And when we are at the leaves, the double black is always nil. So over here, the way we can do it is we can just simply say, well, if the double black is nil, right, then we perform all of this, and then we set that flag to just be false. And we tell it, we already dealt with the nil one. Any double black you encounter from now on is going to be a double black we want to preserve. We don't want to delete it. We just want to remove the double black tag around it. So yeah, I think that's what we can do. The sibling of the node and then its color would be equal to red. Yes, so this is the other warning that we have sort of planted. And it's the fact that if this gets to run, then the node that we would be deleting over here would be like a completely different guy, right? So how how could we change things around? So I think the way I'm going to do it is I'm just going to say, let's create sort of a temporary variable to determine who the new double black is. Initially, it's going to be a null pointer because we are going to theorize there's not going to be a new double black. But if there is a new double black, we simply include it here. So that new double black is going to tell us at the end that if there is indeed a new double black, then we need to make node be exactly that guy. We also need to be careful because we need to sort of how to determine whether or not done. So one of the things here is if we replace node with this new double black, then it means that we should continue the loop. But if this is not what happens, then it means that there was no new double black created, and thus we can just exit, right? So I guess that, I mean, a way to express that is simply else break. right? So I feel it's not that difficult actually. And yes, okay, so this encompasses more what case 3 is trying to say. So is to be if the double black is nil, then we tell the parent of our current node that we are leaving, that say goodbye to your child, because we're gonna take it away. If it's the left child, we tell the parent that its left child is gone, and otherwise we tell it that the right child is gone, and then we delete that child completely out of existence. We know it is a leaf node because otherwise it wouldn't be a nil one, and in that case we simply don't need to care about the children, and then Stevie should be false. So one good thing to do is we're going to include a bunch of asserts across the program. One thing that's sort of very important is to remark that this thing has no left child and that it also has no right child. Otherwise, it means that we're doing something wrong because that thing, this node, should be a garbage value by now. So great. We now have everything in place, which is good. So that's case 3. Now we move to case 4. Oh my god, this is case labyrinth. It's okay. Case 4. For case 4, we have a simpler case, it seems, at least in its condition, because it's only require us to check that the sibling of our node, its color is red. Whenever that happens, and I personally think we need to improve the readability of this. Like, case 3 seems to be rather convoluted. Here we also have the to-do that still has to fix this, so eventually we're gonna have to come back, revisit it, and really oh wait, there's something. What is going on? I think I'm lagging a lot for some reason. Hmm. Uh okay, so we have a ooh. Okay, so I'm trying to check my stream because it is very laggy right now, it seems. And I think that the reason may be that I am transmitting maybe too many packets, like much more than I should. My kbps. Yeah, so my only problem is I think I have here in the OBS settings, it is very, yeah, I'm setting my bitrate to be 6000 kbps. That should be fine, but I am seeing something different here in the software. I'm not sure what's going on. Settings, output, and then CBR. Yeah, CBR, constant bitrate. I think it may be fine now? Question mark, maybe? I think so, right? I think it got fixed. Please let me know if it's laggy at some point in time, and I'll make sure I can fix it. Let me know if it's laggy at some point in time, and I'll make sure I can fix it. Okay, perfect. So let's see. Let's continue. So if the color of a sibling is red, then we need to perform all of these steps, right? So first we swap the color of the double black's parent with the double black's sibling. So std swap of the color of the double black's parent with the double black's sibling. So the sibling of black, its color, and we change it with this guy. Perfect. We swap them. Let me hide this thing. This thing is very annoying. We swap them together. And after that occurs, so we have a node parent color. Yes. So we swap double black's parent, DB parent, and DB sibling's color. After that, we perform a rotation of the parent node in the direction of the DB node. So we don't know whether or not the DB node is sort of is node a left child, and then this is the usual thing with my parent left child, is it equal to me, right? And then we simply say, well, if this node is indeed a left child, then we perform a left rotate on the parent, because it has to be in the direction of the double black, else we simply right rotate in the parent, right? And that's all. So form rotation of parent node in the direction of DB node. Yes. Okay. And finally, so I'm gonna separate them by white lines. Finally, check which case can be applied to this new tree and perform that action. So we basically don't change our double black, and we keep analyzing things the way they are, right? Just now with this new structure. So case 4 was relatively simple, which is great. Yeah, I think most of you are noticing that we're starting to have these sort of like is node left child sort of everywhere, where we need to know whether or not something is a left child. We may want to introduce a helper for that, but that at that point it seems rather unnecessary. We will see. So case 5. Case 5. Case 5. Oh my god, case 5. What? It's okay, bear with me. If the sibling of your node is black, and the sibling's child, which is far from the war, if the color of sibling node, right? So I think we're gonna have to manage things this way. Node T star is far sibling child. We need to determine that beforehand. And once again, if a node is a left child, which is, well, for my parent, it's left child, does it mean? If a node is left child, then we want from our sibling we want to access, if I'm the left child of my parent, then the farthest child of my sibling is going to be my sibling's right child, so right. Otherwise, we want to return the left sibling, right? Yeah, it seems like it. So if the color of the sibling node is black and the color of the far sibling child is also black, I think. Yeah. If that one is also black, and not only that, but we have another condition where we need to do double black sibling's child, which is near to. What are we doing? What are we doing? So now we need to include sort of a near sibling child, and that is going to be basically the opposite decision tree. So sibling of node and then to the left, and then otherwise sibling of our node and then to the right. Right. So and the color of the near sibling child is red. So there is something here where I sort of not sure. Yeah, it's fine. It's fine. It's red. So if this one is red, then and only then will we be able to continue, right? So here with the color, let's see, swap color of sibling with siblings. Okay, so now we need to swap the color of a sibling with the sibling's red child. So that would be swap sibling of node and then its color with the red child, which should be the near sibling child, right? Then perform a rotation at the sibling node in direction opposite of DB node. So we're going to rotate depending on whether or not. So if I'm a left child, I need to rotate in the opposite direction, opposite of DB node. And that rotation sort of, right, opposite direction. So here it would be right rotate. And we rotate at the sibling. Otherwise, we left rotate at the sibling. And after all of this is done, we need to apply case 6, right? So we need some sort of flag that tells us like, oh, we just came from case 5 so that we can also enter case 6. But let me see if we implemented this correctly. Swap the color of sibling with sibling's ref child. So yes, so the color of the sibling with the near sibling's child's color. There you go. And then perform a rotation at the sibling node. So exactly this. In direction opposite of the DB node. So if the DB node is a left child, then we right rotate, otherwise we left rotate. Yeah, this seems right. And finally, we have case 6. And so case 6 is an interesting case because I think that at this point, all of the cases should be sufficed, or like, right? Everything should be fine at this point. And I think that what we can do, since after case 5 we need to enter case 6, we can, after every case, either break or continue, right? We can continue and we can say, okay, I don't want to look at the other cases. They are, for me now, useless, except for case 5, where I need to apply case 6. So if none of the previous cases apply to you, then we are completely certain that you belong in case 6. And so that way we can solve sort of both problems in one go. And yeah, hopefully that's gonna solve it. Hello to everyone that's joining the stream. There's 6 people watching. Yeah, this is incredible. As the title says, we're coding a memory allocator from scratch. Currently, we're not working on a memory allocator per se. We're working on red and black trees. And the reason we're doing that is because we have decided to use that as a data structure to build our memory allocator to keep track of the free blocks. I'm not very familiar with red and black trees, never really used them. I've always used ABL trees because, I don't know, I've never really needed a red black tree. But it just so happened that red black trees are more memory efficient than AVL trees. Thus, we're using it for the memory allocator. And since we're coding the memory allocator from scratch, that implies that we also need to have a from scratch implementation of a red black tree. And that's why we're working with the red black trees. Insertion has been completed for the red black tree. Find has also been completed. Now we are moving to removal. And removal is removal is a serious situation, right? Removal is a little bit of a problem. So that's what we are working on right now, and yeah. So we have case 6, right? We have case 6 is it really doesn't imply anything other than that. And what we're going to do is we swap the color of the double black's parent with double black's sibling color. Okay. Swap double black's parent with like the color with the double black's sibling color. So the sibling of node give me its color. Then perform a rotation at the double black's parent in direction of the double black. So perform a rotation in the direction of double black. So if I am a left node, then I need to left rotate my tree in my parent. Otherwise, I need to perform a right rotation on my parent. Right. Then remove db sign and make the node a normal black node. Oh, okay. So case 6 sort of is a dead end. Like once we reach case 6, we know that we're good to go. So eventually we're gonna have to include a break over here. Swap color of db's parent with db's sibling color. Perform rotation of db's parent. Remove the db sign and make the node normal black node. So if that ever gets to happen, it means that making it a normal black node would imply. What does this imply? Like, does this imply that if it's a nil, it just gets to live its life? I think that's the case, right? So this is exactly what we have up here. So if it is nil, then we simply need to remove it. Otherwise, nothing happens because there's no label that we're storing other than the implicit label of being the node object. Great. Remove the db. And after that, we need to change the color of double black siblings far red child to black. What? That means that the far sibling child, we need to change that to black. So we need your color, fast signaling child. So sorry, your color to now be black. And I think, ladies and gentlemen, that completes the remove function. I'm pretty sure we made a mistake along the way. There has to be something that we did wrong along the way. And so we, before the algorithm also had replaced us, so all of this, I think, is the final. Yeah, this is our sort of like first version. So great. This is a good milestone we have achieved. We still, I'm pretty sure this is wrong somewhere, right? Because it's a very big function, has a lot of cases, has a bunch of stuff. So we should now test it, and now we're gonna proceed to the debugging. It is a little bit late, but I promised you guys that I was going to complete this function. Like we were all going to complete this today. It is our goal. And no matter what happens, rain, thunderstorm, sun, snow, we are going to finish the remove function today. Debugged, completely working, tested, absolutely everything. Nonetheless, I've been sitting here for 3 hours, been streaming here for 3 hours, and so I think it's an appropriate moment to take a break. So let's take a break. I would say let's take a 30-minute break. So I'm gonna be back at 10 p.m. PST, and yeah. So stand up, grab a coffee, go maybe do something else in the meantime, work on something you want to work on, and I'll see you guys in 30 minutes, or well, more specifically, 33 minutes. Okay. Before that happens, so I wanna sort of include that into the little stream that we're gonna have 10 p.m. PST. And great, all right. See you guys in 33 minutes. All right. Hello, everyone. Welcome back. Um, to whoever these two viewers are. I'm not sure, but today we're going to continue. Well, not today. It's only about like we were just taking a break of 1 hour because we just finished writing a first iteration of the remove function for our red black tree. And so now, after this break, we're going to proceed to sort of test it, to debug it, to really see that it's sort of making sense. Um, yeah, make sure that it's like working as intended. Okay. And believe it or not, debugging takes a lot more time than the actual act of coding, right? So it is going to be a bit of perhaps a painful journey. I'm not sure. Hopefully not, but we're going to see. Okay. So right now, we have that insertions are correct, allegedly, right? It's a little bit of a we don't know for sure, like completely for sure, but we definitely have some elements, right, to to think it is right. But let's jump straight to the coding. So over here, let me see. I think. Okay, yeah. I think we're fine. I'm going to make. So I'm gonna make the camera just a little bit bigger. Yeah, that's it. Perfect. And I think the code is visible as it is right now. Because if I make it bigger than that, then it's gonna be like it just doesn't look good for me on my side. I think it's gonna be fine if we just do it this way. But please let me know if you cannot see the code. Previously, sort of all the people, all the viewers in the past have not really complained. And so I would assume that it is fine this way. Nonetheless, of course, as usual, let me know. Okay? All right, we're going to test remove. So the way we're going to test it, so first, oh shoot, yesterday. Oh my God. Okay, so it seems like yesterday we forgot to include test find in here. So when we ran it, it said success, but we weren't even testing the actual thing. Yeah, that is sad. Well, I think we're just gonna have to compile again. Oh, what happened? I think I know. CD arbitrary. Okay, we need to enter the arbitrary folder, and now we're going to recompile whatever we have here. Okay, that's fine. And then we simply do test arbitrary. Hopefully, oh shoot. So there's a problem with our find. Actually, I was lying then. Whoa. Yeah, so the find has no, the find has a seg fault. And it seems like we're going to have to figure out what the seg fault is. Okay, that's fine, that's fine. Okay, time to look for our seg fault, guys. This is less than ideal because I thought that we had completed the find, but we just didn't include it in our test for some reason. I am just preemptively just going to include test remove, just so that we don't forget about it. So here inside of, okay, it says bad access. And we enter this bad access as we are trying to, oh yeah, no, this is completely valid. What the hell? Why do we just compare this with Okay, current should be the root. Right, is there a reason why I just didn't make it be the root? That is very stupid. Yeah, it was previously the root in insert, which is the place where we got this code from. Well, hopefully that was the reason of the seg fault, because then it means that our logic was right. It's just that we... Never mind. Well, let's see what happens now. So let's run this. Okay, so not the bad axis, but now we are performing this. Okay, so inside our test, right? Inside our test, we are looking for 11, so it's literally the first one. Okay, I think I'm gonna have to pause execution here, and then we're going to recompile this to make sure. Okay, and then F5 on that. Let's wait. Great. Okay, so we're going to find 15. Why are we finding 15? The val that's being passed is 15, but that should not be the case. Why is val 15? Well, yeah, what? The only calls to find, oh, of course, check the exact matches for these guys. So that seems to find 5, 1, 12, 13, 17, 19, and 21 are there, and there's like no issues. Yeah, now we're looking for 11. And when we look for 11, current one has a value. It is the root, which apparently is 13. So sure. Then we continue here. 13 does have data. So then the lower bound is equal to the current one, and then the current one is equal to its left. So after this, we sort of skip this, yes. Now we are looking for, oh, it seems like it finished. So now it finished. Oh, never mind. It just went back, right? So to the left of that is 5, and with 5 we enter this conditional, and then we skip. Then we continue here, and this should enter this if, yes. So now the lower bound should be 12. Right? You asked for 11. 12 is sort of the smallest one that's still greater than 11 that we've seen so far. So we skip this. And then now, the current one is null. Why? Well, because, right, 12 didn't have a left child. 12 was just like the last one. Yet we... Okay, that's clearly the problem, right? We only return or break out of this loop whenever we find an exact match. And that shouldn't be the case, right? So while the current one is different from null pointer, we're going to continue doing this, otherwise return the null then. And I think that explains why. Honestly, I deserve that. For coding, I don't know why I coded it, like I wrote that, but yeah. Let's see. Assertion failed. Arbitrary.find data, and it should be 13. And yeah, the program is correct. This should not be 13, this should be 12. So our test was also wrong, which is really bad, but it's fine. Let's see. Success. Great. Okay, so our tests now work. Fortunately, there was just a little bump on the road. I'm glad it didn't. It wasn't like a huge thing, right? So now we're going to test remove, right? To test remove, I think we're going to work with the same tree we've been working with. which is this guy, which we're going to have. So the only way we can know how this tree looks is if we do all the process ourselves. But I think I remember looking for this after yesterday's stream just to know if maybe we could use it, because I know that sometimes drawing is a little bit annoying while you wait for me to change colors and stuff. And I found this website by USFCA University, and it allows us to simply sort of go through everything, right? So, and just like generate the random black tree for us. So 5, then 1. It also shows us like the steps that it follows, which is absolutely amazing. Great tool created by the university. Yeah, so 19, and then 21. Perfect, awesome. So this is the tree we're working with, right? Keep this image in mind. What we want to do is we want to say, okay, assert that after I perform a removal, so if I create rb_tree.remove, and then I tell them which node to remove, so insert returns for us the node that was inserted, right? So I'm just going to say, well, node of int pointer 15, right? It's going to be equal to this, and then I'm just going to repeat the same process but for everyone else, right? If I'm allowed to do it, yeah. Control V and then space. Perfect. So now, ooh, what does it say? Evaluate type constant node int. Oh, okay, yeah, of course. So these are constant nodes. Great. So 15. This is 5. This is 1. This is 12. This is 13. This is 17. This is 19. This is 21. And that's it. And then what we're going to do is we're going to start referring to these guys whenever we call remove. So for example, I want to remove 15, I just call remove 15. I pass it the pointer. And let's wait for the C++ extension to, ooh, cannot initialize a parameter of type node int with an L value of type constant. Ooh, oof, oof, oof. Okay, because whenever we pass it to the delete function, we are indeed going to delete it. So I think that we can just change sort of the signature of insert so that it for now accepts just a const node, right? And that way we can simply test remove more easily. That's great. Here we have, ooh. Oh no, okay. This is fine. The thing is that the C++ extension for VS Code is one of the worst things ever because it doesn't highlight the errors when there are templates involved. And it only does it on files that are not the main one. So it's telling me about all of these errors, all of these syntax errors and stuff that we had that we just didn't know were there because the extension is just not able to highlight them. So I guess it's time to fix them. Let's see. Test arbitrary, and over here we have line 169 here. And it says non-const reference cannot bind to bit field color. Oh my god. So we cannot swap colors this way. Okay. That's totally fine because our color is a bit field. We're just gonna do the usual swap. Color temp is going to be equal to our node's color. Then our node's color is going to get overwritten with whatever the S color is. and now the S color is going to be equal to temp. That's really unfortunate though. I'm not sure that's, I feel it would have been neat if we were able to do it the other way. But it's fine. So now arbitrary to remove, and then 15. I feel that for the sake of code readability, let's agree on this. For the sake of code readability, and since this is our sort of general implementation, I think I would want this color guy to just not be bit packed, right? So we can simply use it in a more intuitive way. And then when we're sort of writing this red black tree for the memory allocator where we're modifying it, then we actually use sort of a bit packed version, and then we modify the code to accommodate for it. Because not only are we going to bit pack it, we're going to mask it with the parent to save some information. Sorry, to save some memory. And because of that, we're going to use to make a lot of modifications, so might as well just make color usual field so that that error doesn't bother us and we don't have to be changing every single swap in existence. Yeah, look at all the errors we get rid of. So arbitrary line 175. What is line 175? Line 175, so here. Oh, of course, the color of the node is red, right? Not node red. In instantiation of member function arbitrary, because to here, okay. So, 246. No member name color in node int. So 246 sibling node. Yeah, of course. It's underscore color. And then finally, never mind. Everything's fine now. That's great. So what we're going to do is we're going to use the same system we used to test our insertions. And it's basically, we're going to say, well, does the red black tree that I'm going to pass you is equal to the other tree I'm about to describe? So the tree I'm about to describe is sort of the pre-order traversal of what the tree should be after we perform the sort of removal, right? This for some reason is complaining. What is it now? Okay, it's just that extension is low. Whenever we want to delete 15, let's see what happens. So delete. Okay, we end up with a new tree. So I think that for this one, I do want to make the animation speed a little bit smaller. Great. So what we have is 13 at the root. So this should be a black, yeah. So it's a color black. It should be black, and then it's value 13. Then the in order traversal says the next one is red, and it's a 5. Sorry if you guys cannot see it. I'm gonna try and make it bigger because this thing is super small for absolutely no reason. Yeah. Maybe this way you can appreciate it more. I think so. I think this is decent enough. So 5. Then the next one would be a black node, and that's 1. Then the next one is a colored black node, and that's 12. Then the next one is a color red node, color red, that is 19. And then the next one is going to be a black colored node, that's 17. And then the next one is going to be a black colored node, that's 21. So that's what it should look like after we remove 15. Now, if we continue, so arbitrary.remove, we're going to remove another random element, say 19, right? because 19 is like in the middle of the chaos. So delete 19. Thank you. Let's see, so 19. Remove 19. 19. Then after that, the tree should look like basically the exact same thing, except for a few things that changed. So we have the root 13, 5, 1, 12. Now this doesn't go here. And 21 changed color. Right? So black, red, black, 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 red. Yep, sounds about right. So after this, we want to maybe remove another element. How about we remove the root 13? So once 13 has been removed, we want to have a tree that looks like the following. Remove 13, please. Just going to look for the in order successor. We remove. Okay, perfect. So removing 13 gives us this new tree. It's going to be relatively similar to the one we had, where it is 12 as a root. Now 5 is black. Now 1 is red. Now there's no 12 here, but instead a black 17 and a red 21. Perfect. So what happens now if we delete, say, a leaf, right? How about we delete 1? Then of course the tree is going to be the same, it's just without 1. So we just grab this and we remove from it, we will remove 1. And then it's just 1 is just going to disappear. Right? 12, 5, 17, 21. Yeah. After that, I think we can remove, say, 12 again. Or no, let's remove 17. Right. 1, 2, 17. 17. Perfect. So after we remove 17, the rules tell us that we should delete that guy, and then just shorten it. Okay, perfect. So it should be 12, 5, and then 21, while 21 changes its color to black. Perfect. Finally, let me remove, maybe we can remove 12. And after that, the tree would end up like this. Nothing else? All right, remove 12. And after 12, we simply have this guy. Remove 1, remove 12. We have the color black being 5. And then the red, 21. Awesome. Yeah, okay. And then after that, if we remove 5, of course, we're going to end up with 21 as the root. Just for the sake of completion, I'm going to write it down. We have a tree. I'll remove, what was it? 5. Then we assert that our tree should just be a black root, and said root is 21. Right? Perfect. And finally, we're going to say arbitrary.remove and then 21. And we're going to assert that our arbitrary's sort of root is equal to a null pointer. That is, we don't have a root anymore, and we're completely empty. Let's wait for the C++ extension to do its job. Sorry, sorry, this is not a pointer. There's an object. Awesome. If all of this happens, then we say true. This thing passed. All right, I think we are ready with our test for remove. There's definitely going to be some mistakes, as I mentioned before, but let's have some faith, some belief. Yeah, never mind. Well, we get a segfault now, yay! There's the reason why this channel is Sharif segfaults, and that's because this is the most common mistake I make, and it's one of the more difficult ones to figure out. So, let's pull in the debugger. Let's have a nice attitude to the bad weather and understand what's going on. So F5. Let's see, where do we get a segfault? Okay, so, well, this is fine, so I don't really care about it. Oh my god. Why are we pointing to the assembly code? Whoa, whoa, whoa. Whoa. That is not good at all. Oh. The problem we're having is here. Where we're like pushing back. So it seems like there's a... Where are we calling? Okay, so somehow it seems like... Okay, when we call remove on the root of the tree, or something like that, I don't know, then like things just get messed up. Oh, whoa, 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 what's going on? Let me put this on my... Whoa! Want this on my main screen, please, aerospace, please. Please don't start acting up right now. We're on stream. There you go. Okay, perfect. Okay, that's not really convenient. If I then delete 21, we're gonna end up empty. Great. So let's look at what our tree looks like when we have the tree, the original tree, right? So that would require us to have this guy here. Yeah, there you go. So we insert 15, then we insert 5, then we insert 1, then we insert 12, we insert 13, we insert 17, we insert 19, and then we insert 21. Awesome. So this is the tree that we have. And according to that, we're gonna have to see what is going on in the mind of remove. So let's run this. But first, we need to include a breakpoint on where we want to stop. And immediately after the call is made, we're going to stop. Okay. So F5 to that, and let's see. Good luck debugging. So the node that we want to remove is 15. So it should be, yes, 15, which is black and it has no children. Yes, perfect. Now, yes, okay. So the minimal node is the node right. And then it also doesn't have any children. Oh, shoot. Okay. Yeah, this is not... I think this case is just badly written, right? Rather than saying that the air is this, we only need to say if the air is a null pointer and the current node is the root. Then we know that that's the last thing ever, so we delete the root and then we make the root a null pointer and then everybody's happy. So now we recompile. And let's run this again. So 5. And so we have this, right? Successor, predecessor, both of them should be null, which is indeed the case. The heir should be null. And now if heir is equal to null pointer, which is true, and the node we have is the root, which is not true. So then we skip this if, yes. So now we want to swap the node with the heir. And what's gonna end up happening, and I feel like we would do better if I could have this sort of drawn somewhere. Look at all the trees we've drawn so far. Oh, this is the same tree. Let's go. Okay, yeah, we don't need to draw anything now. We just simply need to use whatever we had yesterday, because that's exactly what we are using to test off. So hello everyone who's joining. We are writing a memory allocator from scratch. And you may be saying this is not a memory allocator. This is a red-black tree. And the reason why we're doing it is we're using that as the underlying data structure for our memory allocator. It is going to be the data structure we use to keep track of all the free blocks that we have around, because we're going to be using a best fit policy. So whenever we receive a request, we're going to go down through the red-black tree and finding the block of memory that can suffice that request and that is the closest to the request's amount. We're coding a red-black tree from scratch because this is a memory allocated from scratch, quite literally, but also because I've always been sort of more familiar with AVL trees, never really sort of knew that much about red-black trees other than their existence. And so now I'm also learning about red-black trees. We're currently coding the removal of a node in a red-black tree, which is full of cases, full of special cases, full of all of this stuff. We finished coding it, but we have bugs. And we have to figure out what the bugs are. So I don't know. Like we just gotta continue coding. Why red black tree? Well, because between AVL tree and red black tree, the red black tree has better memory usage. In fact, an AVL tree has 20% more memory usage than a red black tree. And since we're writing a memory allocator, we don't want it to consume all of the memory we have available. So that's the reason. And for now, so we are simply using this little toy example as a way to debug whatever is going on with our remove function. So I'm going to have it here on the side. And currently we are trying to remove 15, right? So 15 is the node that we're trying to remove. 15. Great, 15. So now we swap the node and its heir. The problem is that this thing has no heir. So then it's gonna segfault. Yeah, okay, that makes sense. So we have an error there. Now we know what the error is. So the problem is whenever we have whatever we want to remove is a leaf, right? If it's a leaf, then I see. Okay, so this should only happen whenever we had an heir. If we don't have an heir, then we don't worry about it, right? I think this can just be condensed to these two instructions, just coexisting and living together there. And awesome. Okay, so once we have this, I think that error would go away, but then we're going to encounter a new one. Mark my words. Let's see. Thank you. We recompile. We run the debugging process again, and let's see. Let's wait. All right. So no successor, no. No predecessor, no. Because we're trying to remove 15. 15 has no children. Now the heir should be null because neither successor nor predecessor. We skip this because we're not the root. We skip this because we don't have an heir. Now we mark 15 as a nil node, right? So we're just gonna mark it here as a nil node. So I'm just gonna put an X to it. While true, we say, well, if the color of our node is red, which is not true, so we skip this case. If our node is the root, which is not true, so we skip this case. If the sibling of our node is black, which is true, and both of its children are black, which is not true, so we skip this. Huh? Why did we go back? Do you guys see that? We like went back in time. Why? Oh, okay. If the color of your sibling is red, which is not true, and then if your sibling is black, the sibling that's far from you is black, which is also not true in our case. So then we go to case 6. Yes. So now what we have to do in case 6 is, according to the guide by Swati, case 6 is swap the color of the double black's parent. So currently the double black is this guy, so double black is you. So swap the color of the double black's parent with double black's sibling color, right? So if we proceed, swap the colors of double black's parent with double black's sibling. So the parent, which is 17, should be here. So 17 should now be black. Yes, it's black. Perfect. And now the right child of 17, which is 19, should be red. Right, so parent, right, red, and 19. Perfect. They swapped sort of colors. Perform a rotation of DB's parent in the direction of DB. Oh gosh. Okay, so now if we rotate it, the tree should look something more like 19, 17, ignore the colors for now, 15, 15, and then we have 21 on the side, right? So now 19, well, 17 is still our parent. I expect so. Let's see. I feel this is getting like very cluttered. So let me maybe, yeah, there you go. So maybe that's better. And then we can compress this a little. We can close the call stack, close this thing. We can close the watch, and then we can expand this a little. Perfect. So now that we, ooh, whoa. Okay, so data is 15, right? 15. So its parent should still be 17. 17 is black. And then it should have no right child. It should have as parent to 19. And then 19 should have the right child 21. Yeah, so that seems about right. We perform the rotation. Then we remove the double black sign and make the node normal black node, which means we simply make this back into a nil. Right? Seems like it. I'm not sure. So this is the one we're working with, where 19 is actually red. So 19 is red, and 21 is also red. Okay, so we make this a normal black node, which, since this is a nil node, it means just delete it. All right. So we're supposed to just delete this guy, and we're going to see if that works. So if it is nil, which is true, then it is the left child of its parent, which is true. And then if it is the left child of its parent, I just want to tell the parent that its left child is no longer. And after that, I verify that I am indeed a leaf node, should be fine. And then we delete that node. We just take it out of existence. Boom, delete it. And after that, we say, well, we are no longer nil, and this is all we have, right? Now the far sibling child, which should be 21, we change its color to black, and then we can break out of here. And so once we change the color of 21 to black, we go back to a normal valid red-black tree. Imagine this was sort of embedded into this little window. and it is definitely a valid red back tree. So then we proceed, and after this, we should be passing the assert. Great. Wait, actually, I think. Okay, what happens if I just let it run? Will we ever encounter some sort of issue? Yes. Okay. you, you guys are watching my descent into madness as we try to deal with the removal of a node in a red tree, because it is the data structure we have decided to use for memory allocator. So, what could be wrong in here? Great question. I don't know. So, by the way, hello to all of the viewers that are tuning in. We're writing memory allocator from scratch. We're working on red black trees because that's the data structure we've decided to use. I'm not very familiar with red black trees, which makes it all the more important that we create an implementation from scratch. And we're currently coding the removal function. Okay. We just don't know where the mistakes are. So let's recompile. Let's recompile this again. That was a redundant trace. Compile this again. Let's recompile this again. It's a redundant phrase. Anyways, and now let's run it. Wait for the problem to appear. It should be a seg fault. There you go. And now we look at the call stack. We see where was this generated. So the remove function, of course, and this was the removal of 19. So the one right after 15. Okay, so we know that the removal of 15 completely works. So let me just delete it from the tree. Delete. Perfect. And so we should end up with something that looks like this. So let me modify our original tree. Let me make this bigger and then remove all of this paraphernalia we've been using. And let's call this out. So 19 is now red, and it is now the root, 19, and then its two children are 17 and 21. So 17 and then 21. Perfect. So with this in mind, is there anything else like, okay, where could we be failing? Let's try to just enter the remove function and make sure that we know what's going on. So this is when we want to delete 15. We don't care about this. We care about 19, right? So currently 19 is this guy. So its parent should be 13 and should be black, yes. Its left child should be 17. We have a problem. Why is its left child? Oh, the parent's left child is 5, which is indeed correct. Okay, that's good. Its left child should be 17. There you go. And it should be black. And its right child should be black and 21. Yes, perfect. So the state of the tree is what it's supposed to be. So great, let's continue. Do we have a pre... Whoa, 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 what's going on? This is the stupidest function I've ever written. What if result? What we initialize result to null pointer and immediately access it? Yeah, what are we doing? This should have been node, right? I feel. Let's see, min node, and then as we travel down the tree, as we travel down the tree, yeah, I feel this is the right thing to do, and this should not be here. And this should just be that. And now we're all happy. And in fact, we don't need to keep track of result. We can simply use node. For some reason, I created another variable. Yeah, we can just do this, right? If we want to discover the min node in a given tree, we just go all the way to the left and then all the way to the right. So if we recompile, things should be fine now. Hopefully. Question mark? Axis. Oh, yeah. Okay, yeah. That flag made total sense before. If this is a null pointer, then I'm going to return null pointer. And same for the max there, right? So if the thing you pass me is just a completely empty tree, there's no way there's going to be a successor in here. So node is equal to null pointer, and I'm going to return null pointer. Perfect. So let's compile again. That should be fine. Now we debug again. Let's see. Oof, let's see what ends up happening. It's 10:47 for me PM where I am. We've been streaming for 4 hours. It's been a bit of a harsh day. So this is node is 15, so we don't really care about it. We care about the 19 case. We find a predecessor, which should be 17. 17 black, yes. And then we try and find a successor, which should be 21 black, yes. Now the heir should be 21, just because we arbitrarily choose the successor before the predecessor. And now this is not the root, so we skip this. We do have an heir. So we swap the node, which would be 19, with its heir, which would be 21. And then we swap their colors. Right? So what we end up with in the case of our tree here on the right is, I'm gonna make this actually full screen so that we can take a look at it better. We end up exchanging these two guys. So 21 takes 19's place, but the color remains the same as what they had before. Sorry, they also inherit the color. So now 21 inherits its place, as well as the color of 19. And yeah, so now we continue. Now, the double black, sort of the evil node, is now 19, because 19 is the one that we want to remove. We know that it is nil, in the sense that it is going to be eliminated, so I'm just going to mark that with an X. And while true, we're going to evaluate these cases. So if the color of our node is red, which is not true, so then we just skip this. If we have the root, we're not the root, so we skip this. Now, if our sibling is black, which is true, and both of its children are black, which is also true since we have nils in a red-black tree and nils are always considered black, then we enter this case. And that's exactly what we should be doing. Yes, okay. So according to the rules, I'm going to pull up the table over here. I'm going to make it a little bit bigger. According to the rules, what we should be doing is, if your sibling is black and its children are black, then remove the double black. Make the double black sibling red. So that's exactly what we do with this line. Sibling of the double black, which is node. We change its color to red. Right? So now we should see 17, which is its sibling, that is its parent. So let me see, where is the node? Node, right? Its parent, which is 21 allegedly, right? 21, and its left child, which is 17, it's red. So yes, 17 is now red, which is great. 17, let's change it here in our drawing, is now red. 17 is now red. And then after this, we continue. right? We say, well, if the color, so the next step is if the double black's parent, 19, is black, then make it double black, else just make it black. So 21 is red, so we just simply make it black. So we skip that one, and then we make it black. So now we should see that the color of 21 is now black. So the parent just, oh, what? Yeah, the parent, which is 21, is now black. Great. And now we need to actually remove the double black. So we need to get 19 out of here. But before that, let me just draw the fact that 21 is now black. And so now we need to get rid of 19. Right? So what that means is we simply remove it. Right? We tell its parent, which is 21, right? We tell its parent that its child is going to go right here. Node parent, right? No pointer. Now we assert that we are a leaf, then we delete ourselves. So we delete 19, goodbye 19, and then set db nil to false. So now that's basically like removing this guy from here. And that's the tree we should end up with. So we continue. There was no new sort of black. So then we just break out of here. Then we continue. And 19's removal should be successful now. Hello? What? What happened? Oh, the assertion failed. That's probably because we have the wrong tree. Let's see, we should have 13, then 5, then 1 and 12, then 21, and then 17. So, oh, I see. Okay, this is about because we choose to replace our node with a successor rather than the predecessor, which means that sort of the versions are going to be a little bit different, though. So I'm just going to mark this here in test remove. I'm going to say test assumes replacement with successor, right? So that's great. It means that we now have a good tree. So now let's try and see what happens with one. Let's try and run it again. Now without any sort of breakpoint, and see if it ever fails. I think it's going to fail since the tests were previously assuming that we are replacing with the predecessor, but that's no longer the case. We're replacing with successor. And yes, so all I hope to see is that this assertion failed, which is sort of great. I do want to know in which one it was. Oh, 19. Brother, what are we talking about? Shouldn't be failing with 19. Oh yeah, we didn't recompile. Sorry about that. Let's recompile. And let's go again. Gonna drink some water. And where do we fail now? A 13, which sort of makes a little bit of sense because, okay, let's see what the tree should look like once we remove 13. So let me copy this guy, and then we're gonna see if the test case, since the test case assumed predecessor replacement and not successor replacement, things are gonna be a little bit different. So when we remove 13, right, we replace it with its successor, which is gonna be 17. So now 17 sort of changes places with 13. And now it's 17. 17. And now what we do in the 17 should actually be red, because that's what the other guy was. 17. And then we're going to have a black 13 over here. Actually, no, sorry, a red 13 over here. That's also the color that 17 had. So now 17. 17. And I actually think, well, let me input this into the program we just discovered earlier in the stream, and see what happens. So we were trying to delete 19. So if we delete 19, the tree they end up with is different. It has 21 and 17 switched up. Yeah, since they decided to make it a little bit different. But now what I'm wondering is what happens when the one you want to delete is 13? Right, do you just... Yeah, so 13, and then it switches it with its predecessor, and then, okay, so it inherits the same color. Okay, sure. So now, let's see. So now what we're gonna do is we're gonna color the 17 as black. Okay, perfect. So now we have duplicates. And according to the rules, what we need to do is we're going to 1, 5, 12, 13, 21, 17. Actually, why am I performing this example when we could have just used what the article uses as examples? That seems like a rather pointless search, but it doesn't matter. All right, let's just finish whatever we had before. So now 17 is the one to be removed, and we now know that 17 is a red one, so is it going to be deleted, is a red leaf node, then we simply remove it from the tree, and that's exactly what happens now. Bye-bye, 17. So this is the state in which the tree should be in after the removal of 13. It should be, yeah, it's completely messed up. It should be 17, then a red 5, then a black 21, then, oh no, sorry, then a black 1, then a black 12, and then a black 21. So this should be enough to get us through that case, and hopefully it works. Let's see, let's recompile. Great, and then let's run it again and see if it fails the assertion again on 13. Of course, it's going to fail it at 1 because the tree we have in our test case is like a little bit different. Now I want to see... Great! We passed the 13 case. So it now means that 1 may be the culprit, but after 1, what we need to do is the following. So let's see. We want to delete 1. So what we do is we exchange it with its predecessor and successor, but it doesn't have one. So this is going to be the double black, and it's a nil node because after its removal, it's just going to become a nil. And so what it says is, if the node to be deleted is a red leaf node, no, that's not true. This is not the root. Its sibling is black, 12, and it has 2 black children. So now we do this. We remove the node in question. So we remove you. Then we make that node's sibling red. So now 12 is going to be red. Now 12 is going to be red. And then if the parent is black, then we make it a double black, else we make it black. So now this guy, we turn it into a black node, right? And then after that, all of the steps are done. And so we have this tree 17, 5, 21, 12. Okay, so it should be instead, after we remove 1, 17 black, 5 black, 12 red. 12 red. Is it me or we didn't have 12 over here? Oh yeah, no, never mind. So 12 red and then a black 21. And let's continue with the rest, right? Now, if we remove 17, we're gonna have a problem. We're gonna find its successor, right? Just 21. And then we're just gonna exchange them. So 21 and 17 exchange places. 21 is gonna be here, 17 is gonna be here. And now 17 is marked as double black and also as the nil node, because its removal will imply that a nil will surface. So now let's see. If the node, if DB node is root, which is not the case, double black, well, it's not a red leaf, it's not the root, 17. If the double black sibling is black, yes, and its two children are black, that's not true. Its sibling is red, that's not true. 17 sibling is black, yes. The child which is far from 17 is black, yes, it's a nil. And the one that's close to 17 is red. Then we swap the color of the sibling with sibling's red child. Okay, so this 12 becomes black and this 5 becomes red. So the 12 becomes black and the 5 becomes red. We exchange their colors. Great. We perform a rotation. What? We perform a rotation at the sibling node in direction opposite of DB node. So the direction in this case would be right. So the opposite direction should be left. So we rotate the tree left. We now change 12 and 5. So 12 is now the root. 5 is the child. So 12, I think it's red right now. So 5 is going to be the, ooh, sorry. So 12 is going to be the parent. 5 is going to be the child. Right? And then we apply case 6. So case 6 is, yes, the sibling is black and the father's child is red, which is true. Now we swap the color of the double black's parent with double black's sibling's color. So they have the same color, so they stay the same. We now perform a rotation at the parent in the direction of the double black. What that entails is just 12 becomes the new root and 5 just accompanies it. So 12 becomes the new root. And then 5 is just accompanied by 12. Perfect. We perform a rotation in that direction opposite of the DB node. Oh, sorry. We perform a rotation at the double black's parent in direction of the double black. Yes. Then we remove the double black sign and make the node a normal black node. Well, this doesn't seem to apply here, right? Because we swap the colors, we perform a rotation in the parents, yeah, in direction of the double black. So we turn it right, and that's exactly what we did. And then after that, we remove the double black sign, make the node a normal black node. So this was supposed to be a nil. So then it just becomes a nil, right? And then after that, we change the color of the double black sibling's far red child to black. Ooh, so it seems like in a code, so these steps don't really describe exactly what we need to do, because once we rotate, right, once we rotate, the far sibling, oh, okay, we accounted for that in our code, because once we rotate, a far sibling is just some random guy now, right? So in the case of 17 that was here, its sibling's child, it would be right. Its sibling would be this nil over here, and its child would be a literal segfault. So we just need to remember who our far sibling was, but then it seems like the code already accounted for that. Let's give a pat in the back to our past selves because we already thought of that. So we changed the color of the DD siblings far red child to black. So now this 5 changes to black. And that is a new state of the tree. So 5. Great. So in a test, this should be 12, 5, and 21. Oh, it ends up converging in the same place. And now I imagine that like they're exactly the same. So now that I remove 12, actually this one should be okay. Let's see. If we remove 12, then we replace it with its successor, which should be 21. So here put in 21, 21. And then when we exchange them, because 12 was the one here, we mark 12 as double black. We also mark it as nil. And we go back to the cases. Our sibling is black. The 2 children from our sibling are black. So now we remove the double black from our node. Since we were a nil node, we remove ourselves. Then we make our sibling red. Make our sibling red. Sibling red. Sibling red. There you go. And finally, if the parent is black, we make it a double black, else make it a black. So now we make it a double black because this thing was black from the beginning. And finally, we go back to 21 since we still have a problem because it's a double black. You say, okay, the double black is a root, then we just remove the double black and the root node becomes black. So it's already black, and we simply get rid of this. So we should have a black 21 and a red 5. And I think it's pretty clear what happens when we need to remove 5. We simply remove 5. That's case 1. The node to be deleted is a red leaf node. So we end up with a black 21. And finally, once we remove 21, we should end up with an empty tree. So I think those are all the correct cases. Let's compile. Let's run this again. Let's see. Hopefully nothing. Hopefully we get to see a success. Let's run it. Oh, shoot. Oh, no. Okay, there's something that went wrong. I'm not sure what it was. It was when we removed 17. Okay. Give me guys a second. I'm going to take a break. I'll be back. thank you for waiting. We will now continue with what we were doing. So it seems like we have a problem now. Whenever on a tree we end up in that removal phase for 17, which I think I can just go back in time to where we were removing 17 here. So before all of this, 17 was a root, right? 17 black, 5 black. Yeah. So let's evaluate what happens after this. This seems like a rather convoluted case. So recompile this, make sure that it's the latest version, and let's begin. Time to debug. I'm just going to include a little breakpoint when we start the removal process. So here, and then 5. Oof, it's almost midnight where I am, so but I promise you guys, like, we were going to finish in this stream the removal. So let's go. For this, we need to. Okay, this one, the node we're removing is 15. We don't care. 19, we don't care. 13, we don't care. 1, we don't care. 17, we care. So what we should be seeing is that the root of a tree, right, should be 17, which is correct. The left should be a black 5, and that black 5 should have in its right a red 12, and the right should have a black 21. So it makes sense. The tree structure is correct. Now we find a successor for 17 and a predecessor for 17, and the successor, of course, should be 21. The predecessor should be 12. Yes. And so now we continue here, and we say, okay, we have an heir, right? But it is not the last node, so we just skip. We do have an heir, right? So now what we do is we swap 17 with its heir, right? So we swap them, and we swap their colors too, but they have the same color. So currently the state of the tree should be our node is 17. It has a parent which should be 21 black. 21 has as left child 5, and as right child us. And the 5 still has as its right child a red 12. Perfect. So the state of the tree, as we expected. Now, according to the rules, we mark 17 as double black and as nil. So now we proceed, and we say, okay. The case that should apply here is precisely, I think, 5, right? Siblings child, which is near to DB, is red. Yes, so it should be 5. So case 1 we should ignore, case 2 we ignore, case 3 we ignore, case 4 we ignore, and case 5 should be a case that's flagged for us. So the far right, let's see. The far sibling, it takes to be nil, right? I guess, question mark? Yeah, no. And the nearest sibling should be 12. Yes. So now we continue. We make the comparison, and we should enter this if. Yes, okay. So now we swap the color between the sibling and its red child, which is the near one. Swap color of sibling with sibling's red child, which is true. And so when we exchange their colors, they go, right, they sort of change. Hello? Oh no. Okay, I made the little drawing, and okay, that's fine. So we simply exchange their colors. So now 5 is red, 12 is black, 12 is black, and 5 is red. And that should be the case after this line executes. So let's see. Our node, which is 17, is still black. Its parent should be 21. 21 should have a left red. Yes. And that red should have a right 12 black. Yes. Perfect. State of the tree is fine. Then after that, perform a rotation of the parent node being 21, at the parent node, no, sorry, at the sibling node in the direction opposite of DB node. So we should see 12 black and 5 red. So 12 black, 5 red. Good. And after that, rotation occurs, which should be over here when we left rotate. We should have a tree that looks like parent being 21 black, then its left should be at black 12, and its left should be at red 5. Perfect. State of the tree, pristine. Now we move on to case 6, because we apply case 6. We swap the color of the parent with the sibling, but they have the same color, so nothing happens, right? After that, we perform a rotation at the parent in direction of the node that we're about to delete. So now 12 takes the lead, right? And 5 is it's still its left child. So we go here, and over here we go. So since we are a right child, we right rotate. Which should be what we see. Is we right rotate, and then puff. What we should see is 21 has its parent, sorry, 17 has its parent 21, which has its parent 12, and 12 should have its left child, the 5. Yeah. Okay, perfect. And it's red? Yes. Okay, state of the tree is fine. Then we continue. And after that, it says remove the double black sign and make the node a normal black node. So 17 is marked for deletion, so making it normal means just deleting it now. We are a right child, actually. So this should be skipped. Instead, we're going to tell our parent that its right child should be not this black. Oh. What? Ooh. What just happened? So, okay, so when I'm looking at the node, which is 17, we have 21 as a parent, and then the right child should be 17. Oh, yeah, okay. So now the nodes, parent right child should change to null pointer after this line. Indeed, changes to null. After that, we assert that we are a leaf indeed, and then we delete the node. 17 is no more. Great, change is db nil. And now our far sibling child, which was 5 all along, is the one we should modify. But it seems like it just got lost to time. I am not sure where we lost him, but this is what generates the seg fault. So let's see where we lose him. Recompile this to make sure. Then we run this. Oh, Clay. Yo, hello. I just saw the message. I don't know if you sort of wrote in the chat before. How are you doing? So right now we're working with removal. I tried to sort of complete my promise that today we were gonna work and then I would be streaming. Currently, it's been a 4-hour, 40 seconds, 40 minutes stream. So we are about to hit the 5 hours. It's 5 hours, and today I started with removal because yesterday I said like, no, we're gonna finish the removal. The problem is, I went and visited the removal page to see like the explanation, and it was absolute hell. It was the worst thing ever. So it was already midnight. I was really, really tired. So then I said, okay, no, let's make an exception. My goal for today was completing the insertion, which indeed we completed. And removal was just like something extra that I wanted to do. But like, no, let's leave the remove for tomorrow. And so today we started with a remove. It's been 5 hours since we started. The code is completed. allegedly. The only problem we have is that there is some sort of error. So now we're like in the debugging phase, right? Where we are applying tests to see if the thing we constructed works. And yeah, it's I'm not sure if it's entertaining, but it is something that we need to do. And right now there is like some random guy that just gets completely lost. Um, in this case, it is the little sort of far sibling of some random node. so so right here, let's see. Let's try to debug this. We get to this line. It's a far sibling. Um, a far sibling should be oh never mind, never mind. Should be 5. Oh, the far sibling child is huh. Okay, so what? Who is my sibling then? So it seems like we're grabbing like the wrong thing. Its far sibling should be. Let me think, let me think. Oh, okay, okay, okay. We need to recompute these variables because case 5 changes the way, changes the structure of the tree, which means, yeah, okay, okay. Which means that once we reach this case, we cannot rely on the variables we had before. We need to recompute them. Yeah, so now this guy's already been declared, so we change it. We change this guy too, and we change this guy too. We don't really stop being a left child or anything because all modifications happen on the other side, but the siblings change. So now after we recompute that, we should be good to go. Okay. Let's see. If we run this in debug and then we wait until we hit case 6, then we should be fine. Let's see what happens. Good. We want to wait until 17 is the one that we're trying to remove. 19, 13, 1, 17. Okay, 17 is the one we want to remove. Then we continue, and then we get to sort of this computation where the far sibling should be null right now. But then after this line, it should be 5. Okay, let's check. It should be a red 5. Red and 5. Okay, yay! So that means that it gets completed. And then, ooh, we passed. Okay. Now we go with the removal of 12, which hopefully passes too. Yes. And the removal of 5. Yes. And then the removal of 21. Success. We did it. Let's go. Let's go. It's been 4 hours and 45 minutes. It's already 11:30 p.m. where I am, and we've been coding since 6:30 p.m. So it's been 5 hours basically, and we finally passed the small test case that we had for the removal in our red library. Let's go! Okay, this is great. Let's take let's take a break. Let's take a very small break because this has been a little bit mental. I don't know how to describe it. I'm very happy though. I'm very happy we finished the remove. Well, okay. Technically, we haven't finished yet because although we passed an entire set of like, sort of this test case, right? This test remove, that is only one sort of test case, right? Like we're just sort of working with one tree. And we perform all of these removals and etc. Technically, to be like 100% sure, we would need to write more test cases. Uh, but I think that um, I may just do that off camera, just like write some test cases. I won't touch the main code. I'll write the test cases, and then uh, on the next stream, we can just run those test cases to see if our code is correct. And yeah, right. But like for now, I think we can fairly assume like it's fair to assume that we have a correct remove. So, oh, this is so great. This is so great because now we have the the trinity of methods, right? We have the three we need. So we currently have brief, right? Returns the element. Let's add as a prize we get to add the doxygen for this guy. So it simply removes the node pointed to by node calls. By node using successful replacement. Okay. It's important to mention this. Use a successor replacement. Great. And so now I think this is, oh my god, I think we're done. We're done with our red black tree. Isn't that amazing? Like we've been battling with it ever since what, 3 days ago or something like that? It's some crazy time. And we're done with it. We're done with it. Let's go to the coding scene. So we add the doxygen for it. We're done. We're done with these three. Oh, it was a it was a bit of a painful path, but I'm really happy how it turned out. I think the code we wrote is sort of well informed. We made the right decisions. Um, I really want to clean up this remove because we made some choices where we were like, all right, like fix this BS, right? Like this thing right here is like completely ugly. This shouldn't be like 4 lines long. So we left some comments to ourselves. And then things like that, like same thing for here, right? Where it doesn't really look that readable. But other than that, I think like the mere fact that our remove works is already great. The other stuff that I'm mentioning is just cosmetic, right? So apply case 6, just like apply case 6. That's it. So guys, I mean, whoever's tuning in, hello, welcome. We are Rising a Memory Allocator. We were coding red black trees, like our own implementation of a red black tree, and we had been battling with it for like 3 days. First day, first day we started with the design of a memory allocator. So this is what the memory blocks will look like. Then the second day, which was yesterday, we started working with the red black tree and created its insertion method. And then the third day, we created the insert and define method. And then the third day, which is today, we completed the remove method, which is awesome, right? Like now we have all of this. And now we're done with the red black tree. I cannot believe I would be saying that. Oof, 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 oof. Okay. As you can see in my computer's clock on the top right, it says 11:30. That's because it's 11:30 where I am, PST time, almost midnight, but it was definitely worth it. So I think now I'm gonna focus on going to sleep. But before that, I think I want to polish the code a little bit more with all of these sections that I promised you guys I would fix. So let's just dedicate like what 10 more minutes to doing that. And then once that's done, we will call it a day. So let's see. We have this. So this part, I think it's completely fine, right? Here is sort of the section where we're getting rid of bubble black, right? Yeah, so I think this goes here as the double black node. Perfect. So case one, this is fine. We are asked to fix this VS because there's like, in order to remove the node, we need to perform sort of all of these operations. And I am not sure how, like, if there's a better way to do this other than, yeah, I don't think there's a better way to do this. I think one thing we can definitely do is, I don't know if you see that every single time we have these like, is it the left child, right? And so we go, right, we perform sort of this comparison, and our code is full of these guys, right? 10 of them. So I think it honestly, if I'm, like one-to-one guys, I believe that we deserve, like, that guy deserves to be like a little small helper, so that now we don't have to create a variable, evaluate it, and then use that variable all the time. We can just simply, like, you know, um, let's see, link swap. So in what section should we include it? Family members, no, because we already have that. Data access, no, because that's shape, no. What does is it a left child enter into? Where could we locate it into the code? Tree modifications, no, it's not. So family members. I guess that we could rename the section to rather than data access, something like sort of node information, and then it makes more sense, right? We can just create a template, type name t, and then we're just gonna have here a void, sorry, not a void, a bool where we just say is left child, and then in the doxygen we have to sort of explain what this does. The brief is simply going to be returns whether or not the given node, whether or not the node parameter is a left child. And whenever we pass that node parameter, we pass a pointer to it. And then what we return is whether or not the parent of my pointer left is equal to the pointer they passed. We have to account for the case when we have a parent that is just null, in which case we simply return, well, that would be like an undefined case, right? So I think we shouldn't treat it. We should just let it crash if we ever call the function this way. So what we're going to do is we're simply going to assert that our parent is just not a null pointer. If we ever call this function and we somehow call it with a parent that's a null pointer, then everything is going to crash and we will know why. Great. So now all of these lines that are something like node, parent, left, yeah, there you go. We can simply replace them with this little function, because it really gets annoying, right? Creating the variable and then doing it again and again and again and again and again, where we can simply say, is it a left child, our node, right? If so, do this. If not, do that. So definitely more readable. And like, given that it repeats so much through the code, it seems like way better in my opinion. So the is LC node. Well, good. Now this guy we need to remove. Now we say, well, is LC our node? If so, then do that. This one we don't really need. If our node is a left child, then do that. And if our node is a left child, then do that, right? So great. And similarly, oh, hello, Necromantic Monarch. Hello, welcome to the stream. What is a memory allocator? Oh, so a memory allocator is basically, as like usually it's something that you get in contact with, especially when you're working with sort of programming languages that are more related to say C++, C, etc. But a memory allocator is basically your program needs memory. The question is, where does it get that memory from? It's not just like the memory appears from thin air, right? The answer is your operating system gives your program a given amount of memory, right? So it gives it, I don't know, if you, whenever the program wants to ask for memory, it could ask the operating system for a given amount. The operating system gives it like a huge block of memory. The problem is that in that huge block of memory, you could fit a lot of stuff, right? You could fit maybe strings, you could fit a lot of data that you sort of want to store in memory and so on. The thing is, as you use that memory, you perform manipulations on it. You modify the memory, you change it, maybe you allocate, or you try to use a little bit more memory, or you say, okay, this piece of memory, I'm done with it, right? I don't need it anymore. Please give it to someone else because I'm not using it, etc. The one that's in charge in managing the memory of your program, all of those operations of here I am the programmer and I need memory, right? Here I am the programmer and this piece of memory, I don't need it anymore, right? The guy that's in charge of managing all of that is called the memory allocator. Precisely, that's why that's its name, because it allocates memory for you, and it also is in charge of freeing or sort of managing the moments where you want to free it. So yeah, it's a bit of a low level concept, which is why it seems kind of interesting to me. And we're creating one from scratch. So that's what we're doing right now. This is not the memory allocator per se. This is an implementation of a red black tree, which is just the data structure that we're going to be using for the memory allocator, so that the memory allocator can keep track of, out of the blocks of memory the programmer has used, which one of them are free, so that when the programmer asks for more memory, we can look for a block of memory that's free and that is big enough to suffice the programmer's request. Right. So that's why we're coding this red black tree. And we just finished. We just finished coding the red black tree, and I'm so happy because it took us like 3 days. Today I've been streaming for 5 hours. And in those 5 hours, we managed to write the remove method only. So, and it was the last one we needed. And just imagine that, like 5 hours to write how many lines of code? To write approximately 120 lines of code, right? It's kind of a little bit insane. 110 lines of code actually. So, you know, it's this is what makes programming interesting, to be honest. And yeah, I don't know. That's exactly what we're doing. And currently I'm sort of polishing the code that we have left. Because now this is what we're going to use in a memory allocator. So it better work well and it better be readable. Since we're going to need to re-implement it in the memory allocator, we're just going to like copy and paste the code again and modify some code. some stuff, because the memory allocator is going to be written in C, and this is C++. Right, so it's going to be a couple of things that we're going to have to change, but nothing out of the ordinary. Yeah. Is LC node? Yes. Okay, I think that suffices. And then the sibling is just gonna make use of our new function. Good. Perfect. So now where's the parent left? We should be seeing. Okay, there you go. No more uses of it. Let's see. Oh, here we go. So if check if triangle. Check if not, it's LC child on node. And then if is LC, ooh, my AirPods are about to die. And they're the only microphone I have, so I have to keep them charged. But let's see. I think we can just implement a function that's RC, so that we can have sort of the complement to both of them. Is RC in here template. Actually, no, I think it's like too bloated of code to just have an src function too. And I think with that, have we replaced all of them? Maybe. We're just hunting all of them. Down. Node parent left equals node. No, brother, you're gonna use the left child function. And you right equals node. No, brother, you're gonna use the opposite of whatever the guy above you did. So tells you node. Great. We go back to this. This is an assignment. There you go. We are left. This just simply changes to this LC node. Well, was the we are left a victim of? Yeah. Okay. So node. Then what else? Right rotate. Wait, right rotate had another instance of that. So this we are left is just LC our node. Yes. That's fine. That's fine. Perfect. Okay, I think we have raised all uses of this. So we simply remove it. Right. Say all right. Bye-bye. And in fact, I think we can simplify this line by just calling link on the nodes. Well, before doing that, I want to check that we just didn't ruin the code. So let me compile. Oh shoot, wait, what happened? I did something wrong. Oh no, wait. What did we do? 438? Oh, yeah. This equals has to go. Yeah, okay. Oof. That scared me a little. It compiles, and then if we run the tests again, test RB3, success. Okay, yeah, no, the behavior hasn't changed, which means we are so back. We're so back, people. Let's go. Great. So now what we need to do is, I think, as I mentioned, we need to fix this BS. And that's exactly what we were doing above. So right here, right? What we need to do now is, let's see. So else node parent right, node parent left. We're going to delete this node. And I was suggesting that we could fix this by simply linking the node's parent with just a null pointer. I just gone, goodbye, right? And linking it in its whether or not it's a left child node. So I think I think our link function accounts for moments where a null pointer is passed. The only way we can check that is by looking at the function itself. So link the to be child. So if the parent has a left, then the to be parent doesn't change, and the to be child. Yeah, so it seems like it accounts for it, which is awesome. Because now we can simplify all of that with this single line. So now we get rid of this, and now we can just write this, right? Oh, sorry. Tell the parent that we're gone, and then delete the node. So now compare that to whatever we had before, which was this like little bit of like a mess. I feel like it's a little bit cleaner now, right? Hope you all can agree. And then we can just copy this everywhere else. Now we can just spread this piece of code. So now we have the root. Yes. So over here we have sort of the same problem. And now the only thing we need to do is change it for these two lines. We linked the node's parent. Null pointer is LC node. Yes, that's exactly what we want to do. Yeah, that seems about right. So let me just get rid of that code. And then we change this nil to false. Perfect. And then after that, there's another section where we do the same thing. I think we can just find them by calling delete node. Yeah, this one is another one. And what we can do is just copy that. So paste that. Then we're done. Yay. Okay, we fixed that ugly code we had before, like that little piece of whatever. And I think now, let me just check we didn't just break everything. What? What happened? Oh no. No matching function called for link. How come? Let's see, 182. Yeah, link, right? Link is the function we have declared over here. No, link. Link is part of tree transformation link. The to be parent, the to be child, and then a bool. And is LC returns a bool. Yeah. So it should be fine. The to be parent, the to be child, which is a null pointer, and then this guy. No matching function for call to link. Could not match nodes T star against std null pointer T. Oh, okay, so yeah, that's a little bit annoying because it's taking the null pointer to be like okay, but there is genuinely no way in which we can change this somehow for it to accept a null pointer. Like it accepts a null pointer as is, but when I specify like when I give it specifically a null pointer, it just complains. C++ doesn't have union type, so it's not like I can do anything about it. I guess we can just go around and simply say like no T star and then like, you know, cast it to that. Not the best of fixes, but it is definitely a fix. So let's just do that. Node star T, node T star. Then the next one, this one, we just convert it to a node T star. Make the implicit sort of conversion. And I think we should be fine now. If we compile, no warnings should arise. Perfect. And then let us execute this once more. Success! Yay! Okay, we had no regressions, and I think our code looks way better now. Yeah. In case 1, case 2, case 3, in case 1. Do we need that? Prove readability of this. So, what's the problem here? I think this is fine. The new DB if color node parent equals color black. Yeah, this sounds fine. Remove the double black node. Sounds great. Case 4, we grab the color, we swap them together, then we continue. So I think this is also fine. Case 5, when we get all of this. Case 6, recompute the children like these, since we may come from case 5, which could have changed the tree's structure. There you go. So we need to recompute them. And then on case 6, we simply swap, left rotate, right rotate, and then we remove the db, and then is db nil, we link it. Perfect, awesome. I think satisfied enough. We have officially completed the red black tree class, which is absolutely insane. As I said, I think we need a little bit more test cases, but I can be in charge of that because I know how boring it is for you guys to watch me write test cases. So I think we're just gonna, we're going to call it a day for today. And the way to do that officially is, I'm going to sort of ignore all of these guys, is by committing it to Git. So git add, and then we're gonna commit. Actually, I think I need to go back a little. Let me add a git ignore here. I just have VS Code to be ignored. And yeah, so git add everything. Let's commit this into some sort of feature. I don't know. Let's feed sort of add red black tree. Perfect. Reset this, and then we're just gonna push it. Yo! So everybody, if you're interested, I currently have a repository where I store the code for the red black tree. Feel free to visit that repository. Like do whatever you want with the code. Code edited here on stream. And from my repositories, where did I look at my repositories? There you go. So data structures, this one. And this guy, I'm just gonna paste it in chat. So over here. There you go. So there you can see sort of the progress we made with the red black tree. Awesome. All right. So this is very exciting for sure. Really happy that everyone stuck around. It's going to be midnight in like 5 minutes for me. So I hope you all enjoyed the stream. And yeah. Oh wait, Zero Nisel? Zero Nisel? Thank you for following. We have 8 followers now. Let's go on a road to 10 followers. Okay. Yeah, I hope you guys enjoyed. So the plans look like this. Bear with me. Um, Now that we have finished our red black tree class, it is time to sort of write the actual memory allocator, right? Because we have all the knowledge from the red black trees and we already have the code. So the only thing we need to do is sort of modify the code a little so that it can fit our use case in the memory allocator. Because in the memory allocator, right, we're not going to have stuff like, I think we use new multiple times here. New, like new node. Yeah. So this stuff, we don't really have it, right? Because we are the ones writing the memory allocator, so we cannot have news and stuff like that. It's going to be in C, and yeah, so we have to modify the code a little, but we have everything already we need. Tomorrow, we start with a memory allocator. Like we've been coding the memory allocator, but like we start with the nitty gritty of the memory allocator. And yeah, hopefully you guys will enjoy it. Tomorrow is going to be a little bit more exciting. It's going to be like exactly what we came here to do in the first place 3 days ago. I'm so sorry, I forgot to update the title. It's his second day on Twitch. This is my third day on Twitch. So yeah, I hope you guys can have a good day. I know many of you are in Europe based off of the time. So, because here is like midnight, and for you guys, it should be morning. It should be like about 9 a.m., 10 a.m. So, yeah, thank you, everyone. Thank you for sticking around. And we'll see you tomorrow, probably at 6:30 as usual. So, okay. Bye bye, everyone. Bye bye. See you.